Does it make you feel like a student again?
Yes, yes, yeah.
I want to plug in my computer. Maybe I'll sit over here. Oh, I hope I can see very well.
I need to plug in mine too.
Isn't that funny? We get used to sitting on certain sides of the room.
True. Or even like I was thinking in the Cannon Center, like, hey, I was looking for people, I was like, there'll be people over where we usually sit. We go there.
I know, we're just creatures of habit.
Mm-hmm.
So did you guys go to lunch all
Yeah,
together?
we just went down to
Cannon
the
Center?
Cannon Center.
Nice. My kids love that place.
You may probably because they can just grab
Because
whatever
they
they
can
like.
get whatever they want, all the treats they've got there.
Yeah, it's true. Some things are good and some things I'm kind of like, what the heck is
Yeah,
that?
yeah, it's true. Yeah, the food's not amazing, but it's okay.
don't know where everybody else is.
There were a couple of them down in the other room just grabbing their stuff.
Hello. Are we gonna bring the table together? This one's weird.
Should we do a horseshoe?
Yeah.
What's best for the way that you
whatever.
have to film?
Well, I've got it set up here, so that one this one needs to stay, and everything else can be fine.
Oh, I forgot. We're doing the video
So
lecture.
is
Yeah,
it-
that's
is it
why
if
we're
we
in
did a
here.
horseshoe this way.
That's
So
fine.
we can all,
Sure.
How do you
Do
do
that?
it?
just a,
Yeah, this just feels
Like a
way
U.
too, I can't see people.
Donnie at the front of the horseshoe.
I don't know what Janie's gonna throw at me.
I really need to start bringing my stress balls. And just toss them back and forth.
I haven't found any stress stuff.
How
for
many do you
lately,
have
yeah.
now?
All right, I probably have about 35. I've actually started rotating them because my office was starting to look like a toy store. So I've had to kind of put a few away and I'll bring a few out.
So do you stay here?
I think that one
That.
stays.
Was it two
So-
or just one? And just put them
That
on
one
the
wanted
side?
to use
Just leave
that.
the out ones, okay.
Just
I just have to
everything
stop my computer.
As long as, will people on this side be able to see okay? Because they'll be kind of perpendicular to the screen.
Yeah,
I think so, that's where I'm planning on sitting, is perpendicular to that.
that's how it was in Sterling. Yeah, because that's how we sit on that
That's how we
side.
sit there.
Okay.
Okay, so then this one, you can
Actually, maybe
swing.
we'll use the outside tables. and
Yeah,
make
we'll
these
just
ones
swing
inside.
this one around. I'm just gonna put these
And
down.
Liz brought these for you.
Oh, nice.
We want to push, well, oh, because we're centering around the. Maybe I'll be right here. Yep. Okay, so kind of thing. As I was like, looked in my closet, I was like, oh, I have a really wide shirt. And I wear a striped shirt underneath it. And so I said, oh, I don't want to wear all those things.
Sorry,
Put a
guys.
sweater on.
Right.
Then I saw you and I was like, I'm your plan.
Well, I think we're gonna do it because
I know, and so, oh, that's, so I was like, that's awesome, basically, that's perfect. Okay. Okay, so Jamie, where can I drop this little
I'll show you.
fella?
Walk with me because I want to take this stuff back to my office.
Excuse me, Mike, I promise I will return this at the end of the day.
What?
So just bring that and we'll put a sticky note on it that says for Sterling.
You gotta remember to bring mine back. I'm gonna be doing it in white reading.
What, the intros, the stats thing? Yeah, I've got
One
it.
was just a game.
I don't want this stuff here.
Mike.
Got everything?
Yeah, this Liz someplace, where's open? This one open?
Alright,
I think so. Unless Mike was there, I don't know. I'm here to pick the place now. Chairs. All right, put Liz over there.
Did you get your computer? Okay.
Yes. I can't figure out my own life. I don't know what I'm doing.
Well, I was either like, gonna do it sorry, or last night, I got home last night, like, I didn't go all night yet, for I'm drained today.
That's amazing. I went home and like, you read a book.
Wow.
Not a real book, but.
Like a book of your own choice?
Yes, like a novel.
Oh.
I
Are living
know.
on the edge.
I am. I was like, I can't do
Who's
this.
this? Liz's?
That is Liz's, yes.
Afternoon, do we want?
I mean,
I should be good for power.
Take that. Any more tables down the back here?
Are we going to be using books today, like examples?
Just sit to your right.
We'll have a few, yeah.
Not here.
No one's here.
You want Liz to sit down there?
Yeah, we can sit down. Or I can slide down and let Liz.
Slide down.
We need to pull one more table.
We didn't know it's hard to get out.
Do we have enough spots?
We need a spot for Liz.
I got one there.
How did we set it up last time? How did it seem like you?
I think we had that one table.
More centered on
I
the.
think we had that one table.
Sorry, Donnie.
Is Liz here?
She's
here.
coming.
Okay.
She'll be here in an hour.
We should make her sit at this, like,
In the
inside
middle. In the
table.
middle, like-
You're so mean.
That's awesome.
Just put it out on a little chair there. Oh, bless you. Oh, give us a hug. Oh, what? No. Wait, I don't think it works.
There's nothing sadder than a dead pen. Especially if it's a good one.
Thank you.
Yeah, they do. So just walk back to where the fridge is, and I think they're, I think they're in the stand-up cupboard. It is warm in here, we need to turn down.
We can't, there's no control in this
There's
room.
no
Stomach, hot room.
No.
It's a bummer.
Stay awake.
Because this room,
Stay awake.
sometimes these classrooms get really warm.
All right, so we have Jody on our prayer and Mike on our spiritual thought. Are you guys
Good.
ready
Good.
for those? Okay, well, let's get started.
Can we drop the,
We should start doing
can we drop the screen? It's just
Sure.
a lot of glare on the computer. Thank you.
All right, I will offer a prayer. Our Heavenly Father, we bow our heads and are grateful for the opportunity we have to gather this afternoon and to increase our knowledge and analytical understanding and invite the Spirit to be with us and to be with Donnie to articulate these principles and procedures to us in a way that we can retain and we can be helpful with each other in terms of the questions that we're asking and help one another understand. Father, we pray for our colleagues who aren't with us and ask a blessing upon them, that Liz can return to us quickly and not miss too much. And pray that thou will go forward with us after class today, that we can remember the things we've discussed and be able to do the word that's been sung. We love thee and we're grateful for all the efforts that have been put forward amongst ourselves and to our instructors, and ask a continued blessing to be on them and their families. And this we ask in the name of Jesus Christ.
Amen.
Did your son win?
They don't keep score at this age,
Oh, that's
so
good.
Okay.
yeah.
They never
Third.
kept score.
He's a third
Maybe
grader.
I would like sports.
They played well though. That's good.
I like a cup better than I even like
Ah, there you go. I like that they don't keep score. Why didn't you do that when I was younger?
I like that when they have more than
Score.
one winner. I have more than one winner.
Oh, no.
First winner, second
Keep
winner,
score.
third winner.
Score.
Have
There's a-
winners.
There's a
I
winner
like
and a
those
loser.
I'm horrible at all of them.
Our family fought so much fuss when we started having first, second, and third winners. It was amazing.
All right, my spiritual thought. So this is actually something that I read yesterday, and it stuck out to me because of what we've been talking about, not only in our multicultural class, but here, because I've probably told more than a couple people that learning statistics for me is almost like learning a foreign language, because once you think you've got the basic idea down, there's always a rule or a conjugation or something else that it doesn't quite make sense.
Yeah.
And yeah, and so I've been thinking about language, and we talked about the significance of language and culture in our multicultural class. And when I read this, it's one of my favorite scriptures, but I saw it in new light yesterday morning, and so I thought I'd share it today. So this is Nephi in 2 Nephi chapter 31, where he's speaking plainly about the doctrine of Christ and the baptism of Christ and like that. And he says, "For my soul delighteth in plainness. For after this manner doth the Lord God work among the children of men. For the Lord God giveth light unto the understanding, for he speaketh unto men according to their language, unto their understanding. And I thought, it touched me for several reasons. He gives us light unto our understanding, and he speaks to us in our language, and not necessarily the language of English or Spanish or German, but I think that's true as well. But he speaks us unto us according to our language, unto our understanding, in a way that we get it, and a way that makes sense to us. And I love that, and I have felt that and understand that in my life. That he speaks to me in a way that I get and I understand. I think he does that with all of us, and that's how we learn. And it's through the Spirit, of course. The Spirit's the teacher. So I share that in
Amen. Thank you. Okay, so let me just pull up here. Let me show you guys. We are streaming live right now. So as I mentioned, you'll have to watch your verbal behavior. Visually, you can do what you want.
Thousands of viewers.
Yeah, for sure. So if you want to go on there and give me some thumbs up, I'd really appreciate it.
Likes? Was that number
Yeah,
likes?
yeah. Johnny fits the perfect.
Did you do that last night?
No.
Oh, okay.
No, sorry. I wasn't ready for it last night.
Okay.
So now we know it's an option.
Okay, so how's everyone feeling? We're in the last third of your weekend. Things go well with Mike's class. You guys feeling refreshed after your walk and lunch?
No, but,
Refreshed, that's the word, right? Not tired and worn out? Okay.
Lack of sleep, nothing like this, right?
Does anyone remember what we covered yesterday? What test did we look at?
Van, Whitney, whatever, the college.
Wilcoxian.
Okay.
Was it Wilcoxian or Wilcoxon?
Wilcoxon.
Oh,
Van with EU.
Oh, there's another one, why can't I think of it?
Wilcoxon, signed rank.
Two dependent.
Oh, the one T,
T-test.
the one T, right? Whatever it's called.
Two-factor T-test.
I'm just making names up at this point.
Or dependent t-test.
Dependent t-test.
Okay.
Those are the three we did.
And we did a little review of independent samples t-test, right?
Yes.
So today, we're going to build on what we've covered with the t-tests already. And we'll go from there. So we're going to start with analysis of variance, or Anova. And then we'll get to the Kruskal-Wallis test, which is like the, I can't remember now if it's like the Governor Wallace ACE or if it's Wallace like this. Hold on. Oh yeah, it's this, I got it right. So, and then we'll cover chi-square tests in the latter half today. Sound good?
Is the Anova file, it was updated, up to date as of last night, right?
Yep. Yeah, I updated it yesterday, so you can download that. Well, if you download it then, it should be up to date, or you can get it now. So we will start with those slides. Okay. So let's erase these top three here and talk for a second about our independent t-test, just as a reminder, and what are the situations in which we use the independent t-test?
There's a dependent variable and an independent, right?
Okay.
Variable.
And what kinds of variables are they?
One, you mean of like nominal or?
Yeah, what scale of measurement are they?
Continuous is the dependent,
Good.
and then I don't know what I know what it is, but
Interval or
categorical
ratio,
is
right?
the independent.
You can call it, yeah, categorical, or it's a nominal variable. With how many groups? 2. Okay, good. That's our independent t-test. So we use that to compare the means of two groups on an outcome variable that we're interested in. So what do we do if we want to compare more than just two groups? So let's look at what examples have we been using. So, well, in the example we used last night, we were looking at the balance between those treatment and control groups in our cards example, right? And we were looking at the variable socioeconomic status to see whether there were differences in the treatment and control group. But what if instead of having just two groups, maybe we had three groups? We were looking at two different treatment groups. We might have treatment 1, treatment 2, and control. So let's say in the example of Kristen's study where they're looking at the study groups, right? So let's say the first treatment was a study group that was an equal number of males and females, and the other was a study group with more females or something like that. So now rather than having just two groups, we have three. So the question is, if we want to know whether there are differences in socioeconomic status across these three groups, is it possible that we can just use maybe more than one t-test, right? We could do a t-test to say, are there differences between that group? We could do a second t-test to say, are there differences between those two groups? And a third t-test to say, are there differences between those two groups?
Doesn't that compound your errors though?
Why would that compound our errors?
Because you're looking at yeah, it does.
Is it because it's more likely to be significant if you're just comparing the
So let's think of,
type 1
sorry.
error, like you'd have more evidence you have a type 1 error where you, okay.
So if we were to do just this one t-test, right? So to determine whether there's a difference in socioeconomic status between those in treatment 1 and treatment 2, we could do a t. And what would the null hypothesis of that t-test be?
There's no difference.
That,
They're equal.
that the mean, let's call this m, so the mean of treatment 1 is equal to the mean of treatment 2, right? And if we set our alpha level at 0.05, then what is the likelihood that we'll commit a type 1 error in this t-test? 0.05, it's 5%, right?
Right.
Okay. Then, if we do a second t-test to compare these two groups, essentially we again have a 5% chance, in that one individually, but when we're combining these things, basically what we're seeing is that we're increasing the likelihood of saying that there's a significant difference when there isn't. That we're just observing that due to chance or due to the sampling error that we have. Okay? So I've got a slide with a little bit more detail on this. But let me first show this is our flow chart that shows, okay, we're examining differences between multiple groups here, so two or more groups on a single outcome variable. Are the same groups or the same participants being tested more than once? No, right? Because we're measuring this group once, we're measuring this group once. How many independent variables are we dealing with? We already said that we were dealing with one. This is our group variable. Okay? How many groups do we have? In this case, we have 3 groups. So we go here to 3 or more. Our outcome, socioeconomic status, is a continuous variable. Okay, so it shows here that we would use the one-way Anova. Okay? However, if the outcome, instead of SES, let's say from yesterday we were using that education expectation variable. right? Where 1, or maybe was 0, was less than college degree. 1 was a college degree, and so on, right? Where this is an ordinal variable. For this, it doesn't meet that assumption of having a continuous outcome, so we would instead use this Kruskal-Wallis version of the test.
And SES is continuous because there's just.
Well, I guess I was assuming it here. It would depend on how it's measured. But in the example that you guys had from problem set 1, you had, trying to remember, you had a composite, some kind of composite measure of SES that went from like 1 to 30 or something like that, right? So something like that would be an interval level measure, right? So we consider that continuous. But if you measured this in a different way, you could measure SES in a way that's more ordinal.
Like yes, no, free or reduced lunch, yes, no, right?
Well, yes, no would not be ordinal. What would yes, no be? It'd be categorical. Yep. So that wouldn't work here. But actually, so you can see what you would do here. If you had a categorical outcome, you would drop down and do a chi-square test. So instead now you have one independent variable that's categorical, and you have one dependent variable that's also categorical. And so you use a chi-square test of independence to use that. Actually, it's wrong on the chart. I need to change it here.
And that would be a non-parametric test, correct?
Correct. Yep.
Is the Kruskal-Wallis?
Kruskal-Wallis is also non-parametric.
And we use non-parametric when our assumptions aren't met, and particularly usually abnormality. Is that?
Yes. Right. Because if our assumption of homogeneity of variance is not met, what can we do?
You go to the F.
Yeah, we can use, we stop, drop, and roll. And on that line, we're using what's called the Welch's, not Welch's grape, but the Welch's T or F correction. Right? Okay. All right. So I keep standing like right in front of the camera. I have to come over like here or something. So the conceptual understanding of what analysis of variance is doing, right? So the full name of the test is analysis of variance. They shorten it for these first few letters in each of the words, Anova.
We don't shorten Kruskal-Wallis, but we do.
Well, you can, but no one will know what you're talking about. The
Because no
K-dub.
one's name is
K-dub.
because no one's name is in it.
That's why.
That's true, right?
That's exactly right.
Although sometimes people shorten that Smirnoff test. They call it the KS test. Yeah. So I think we've compared this. Yeah, all right, we're gonna see it here. So back to this idea of why not just use multiple t-tests. So if we were to run each of these t-tests independently, each of them would have a 5% error rate. To calculate what the total error rate would be for these combined 3 tests, we are considering something that's known as the family-wise error rate. Right? So that's basically the likelihood of type 1 errors that you have from your combined set of tests that you're running. Okay, we call that a family-wise error rate. And there's actually a formula for calculating. It's not simply 5 plus 5 plus 5. It's close to that. It's slightly lower than that. So you take 1 minus 0.95, and this, 0.95 is because that's referring to the alpha level that we've set. If you set the alpha level at 0.10, then instead you would multiply this by 0.9, okay? But since we've got this at 0.05, then we multiply by 0.95 and take that to the power of however many tests you're running. So you cube that, okay? Someone wanted to calculate 0.95 cubed for us?
14.3.
No, well, that's the final answer. So that's 1 minus. So, you smart guys.
So, 15.
Nice try.
We're just jumping right ahead.
Oh, and you want to do 1 minus?
So, well, let's do just 0.95 cubed first.
I got 0.857375.
0.857,
Agree.
right? And then 1 minus 0.857, Anthony? Yeah, so if we conduct one t-test, basically we have a 5% chance of getting a type 1 error, right? Which is what again? What is a type 1 error?
Then a false positive.
It means we would reject the null hypothesis when we should have retained it. Okay? So now our family-wise error rate, if we were to run 3 t-tests, we would have a roughly 14% chance of committing a type 1 error, right? That's pretty substantial just for having 3 tests. In some research, you'll have dozens or even more than that of tests that you're running. And so we really have to be careful to consider what's going on here, because we could make conclusions just based on the fact that we're inflating our error rates.
This may be a dumb question.
Go ahead.
Why is there a named conceptual thing for something you shouldn't do?
Well, the family-wise, you mean?
Yeah. Or when is this?
Well,
when
because this is, so think about it in a way that it's something that no one had thought about at one point in time, and then some smart statistician came around and said, hey, when we're doing all these t-tests, this is what's happening, and I have to come up with a name to call what's going on here, right?
The more kids you have, the more problems you have.
There it is.
I know.
There you go. I like that.
Well.
I like that. Okay.
That's for.
So, Mark Wahlberg is always concerned with error rates, right? He doesn't like type 1 errors.
Oh.
So Anova basically is an approach that we can use to eliminate this, right? We can test all of these things simultaneously within analysis of variance that allows us to keep our error rate at 5%. So that's the big advantage of analysis of variance over multiple t-tests. Also, it's more parsimonious, which is a fancy statistics word for simpler. Right? There's another one. That's another word. Yeah.
Parsimonious or
So-
simplified.
Yeah. So we like things that are simpler. It's kind of like the statistician's Occam's razor, right? If you could do the same thing in 2 different ways, the simpler of the 2 things is desired, basically, right? So that's what analysis of variance does for us. So basically, we're comparing means across multiple groups. And our null hypothesis then, so now we have 2 groups, right? So we have mean 1, mean 2, and mean 3. Sounds like a Dr. Seuss book or something. And our alternative, I guess I should use mu here.
When do you use the capital M and when do you use the mu?
M is for the sample, that's for the sample mean.
Okay.
And the mu is the population mean. And so for hypothesis tests, we're inferring that these are results for the population, so we use mu.
Sorry.
Yep. So our alternative hypothesis then is that it doesn't necessarily have to be that all of the groups have different means, but it's just that it could be that there's a difference between those 2, but groups 2 and 3 have the same mean, right? Or it could be that groups 1 and 2 have the same mean, but groups 2 and 3 have different means. Oh wait, no, that can't be right. Because if those two are equal, then if those two are equal, so I guess it has to be that way, right? Because mathematically, if 1 and 2 are the same, then if 2 and 3 are different, then 3 and 1 are different by default, right?
You're right.
So, okay, so it has to be that.
Oh, yeah.
So you can't really have the second two. So the alternative hypothesis will look like this then. So then Anova has a couple of different steps. The first thing that we do is referred to as, okay, more fancy words coming, guys, an omnibus test. I guess that's the vehicle you use to drive your family-wise errors around.
Just keep them coming, Donnie, because it'll keep us entertained. So
Well,
that's-
and at this point, like, the farther you guys get into your weekend, the easier the laps come. So it's really good to have Saturday afternoon.
I mean, all these suburban.
So then the second step, basically the omnibus ANOVA is testing this, right? It's saying, are all of the means equal or are there some differences? Okay? The follow-up to that is, if you find that the null hypothesis isn't true, that there are some differences within your means, then you go to a second stage and do something called post hoc test.
Oh, yeah.
Okay? And this is basically, I'm going to go back to our null hypothesis. Let's say we now have more than 3 groups. Okay? At this point now we could start seeing differences between just certain groups. Right? Because maybe all these two are the same, but those two could be different from each other, right? These two could be different. Anyway, now we're starting to compare a number of different groups, and it could be the case that, you know, just these two are different from each other and all the rest are the same, right? And that matters a lot to us because if we're going back to Kristen's question, right, we had treatment 1, treatment 2, I'm going to add another one. Say we had 3 treatments, so 3 different study groups. In this one, there was equal male, female. In this, there were more males. In this one, there were more females. And in the control group, they're not participating in the study group, right? So it's not sufficient to just say, we know that there's different means between these 4 groups. We want to know which means are higher. We want to know which means are lower. We want to know where the differences are, right? So that's what the post hoc tests do. The post hoc tests help us to identify, it's like running individual t-tests for all of these, what we call pairwise comparisons, right? So pair meaning we're comparing 2. We're comparing a pair of groups, right? These are all of our pairwise, you know, you can have the other ones as well.
So you said, so doing this is like running t-tests on each of our groups,
Mhm.
but but we don't have to worry about the family-wise error.
Because it adjusts for that.
Okay.
Yep. Okay. One of the other advantages of analysis of variance is that you can now start to add more independent variables. So initially, in this example, we had 1 independent variable, 1 dependent variable. Well, it might be the case that we want to know how the outcomes might differ for males and females in each of these groups, right? So we might have the one variable called gender and the other variable called group. And we can include both of those in our analysis of variance, but still looking at our whatever our dependent variable is in our outcome.
Is that basically at the same time, or is
Yeah,
that
it's at the
taking-
same time.
Okay, so it's not a different test per, it's just,
Nope, it's at the same time,
Okay.
and we can now, this is the first tool that we've come across that we can start to assess the interactions between variables. Or maybe the other word I should use, right? We talked about, remember on our first day we looked at the conceptual models So we have our explanatory or outcome. We looked at some moderating and some mediating variables, right? You remember these? So a moderating variable is a variable that changes the relationship between two other variables, right? So initially, we were saying, what's the impact, or what's the effect of their group membership on, so their outcome that we're interested in is their performance. Okay? So how does participation in the group change their performance? And the interaction or the moderating variable could be gender, that says, well, how much impact group has on performance could vary by gender. It could be different for males and females. So here we're testing the interaction between these two variables, gender and group.
Just to be clear, moderating versus mediating.
Uh-huh.
the difference?
Mediating is where you have one variable, so your explanatory variable, that impacts the outcome through another variable, right? So the example that I sometimes use from my own research comes from some of the charter school studies that say, what's the impact of attending a charter school on student performance, right? And there's this model within certain charter schools that's referred to as a no excuses model. Have people heard of this before? So does anyone know what a no excuses charter school is?
They don't accept failing grades. Maybe, is that the?
So they have a fairly strict disciplinary policy, really high expectations for the behavior of their students. Also, a lot of these come with things like parent contracts to say, you as a parent, by enrolling your child in this school, you're committing to do this, this, and this, whether it's helping them with their homework or sometimes spending a certain number of hours in the school. But anyway, so whether or not a school has this type of no excuses model within their operating framework, basically some of the research has found that charter schools do have an impact on achievement, but it's through this no excuses model. That basically you take that away and they're not doing much else to impact student performance that's different from the public schools. And so it's impacting it through, so a mediating variable would look like this, where charter is leading to this no excuses model, and that's then causing the change in student achievement.
So that makes sense. They call it mediating because it intercedes. It's the mediator between the two.
Yep, exactly. Did you have a question, Memo? You're just chilling. Okay.
No, just relaxing.
So we won't get to this type of ANOVA today. We will cover it next time we meet, where we have more than one independent variable.
So can you give us an example of a moderating variable?
So this was the gender.
Okay.
So in the charter school research, there is a good example of a moderating variable. There have been a few studies that have kind of summarized the research on charter schools across the US. And what they find is that if you compare just across the board, on average, charter schools perform about the same as traditional public schools. But in urban cities, so where some of the initial charter school models started, there was a big program called Harlem Children's Zone in Harlem. There's a number of schools in Washington, D.C. that perform well. These are areas where traditionally the public schools were run down, didn't have much support, and so basically whether the charter schools are located in these urban areas that have had more difficulty traditionally with the public school system, that's seen as a moderating variable because it changes this relationship. Where basically what you see is that in urban areas, there tends to be a positive link between charter school attendance and student achievement. And outside of urban areas, there's basically no relationship between the two. So the urban variable is changing the relationship between those. But it's, yeah. Does that make sense? Okay. So we'll get to factorial Anova next week, or the next time we meet. It's actually, we don't meet for 3 weeks after today. And let me, first week of March is the next time we meet. Remind me before we leave to talk about the surveys, your surveys that you worked on last semester. I forgot to do that yesterday, and I want to just say a couple things before you guys go. Okay, so there are traditionally 2 different ways of getting the groups within our categorical variables. So the types of groups that we see in our independent variable, the most common thing that we see is that these groups are sampled from different populations, right? So if we were doing a study, if we were comparing males and females for something, right? Basically, this is a situation where we have our population. Well, you have your population of males and your population of females. And you've sampled from those 2 populations, and then you have your sample of maybe 50 males and 50 females, right? And then you're comparing the outcomes for those 2 groups, for the males and females. The other way that we can assign, or that groups can be established within a categorical variable, is through what we talked about last night, is through random assignment. So here you would have your population, and you sample from your population, 100 people to be in your sample, and then you randomly assign 50 to one group and 50 to another group. Okay?
Which is the most ideal.
Which is the most ideal, yeah. But traditionally, it looks more like this, where we're sampling from different populations, right? Usually when we have data, when we have a gender variable, we're assuming that those 2 genders are coming from 2 different populations, right? Because what we do with an independent samples t-test is we compare the means of those 2, this would be the male distribution, the female distribution. We're assuming that they're coming from 2 separate populations, right? That's sort of inherent within the structure of our t-test and also the Anova. So with the Anova, what we're doing is we're comparing now 3 distributions or more, for however many groups we're looking at. 1, 2, 3, 4. All right, well, let's get into the details of analysis of variance. So we need to start with a little bit of change in the notation that we've used to this point. So up till now, do people remember the difference between a large N and a little n?
One's big and one's small.
Yeah.
Large N was the population, isn't it?
So large N up till now has been referring to our population, and little n to our sample, right?
Of that population.
There's a slightly different notation used in analysis of variance because we have multiple groups that we're dealing with, and so we need to know different sizes of the groups. So in analysis of variance, capital N is referring to the total number of participants or the total observations that we're dealing with. So if we're looking at, well, let me say this one first. So that's the total number of observations, and the little n is the total number per group. So let's say we were doing a study and looking at students at BYU, and we wanted to compare those, something across students who are from Utah, who are from outside of Utah but from the US, and from those that are international students. Okay? And we have 50 from each group. In this case, our capital N for the study would be 150, and the little n would be the average per group, which they're all equal here, so it would be 50 for our little n. And that's important because we use these both in the formulas for calculating our
So it's an average
statistic.
number, it's not.
So it's the average per group. So if you had 53 here, 50 and 50, then the little n would be 51.
Unless you say N1, then you're talking about 53 now.
So.
Yeah, exactly. Yep. Yeah, so
that's
that's important. So we can also, because a lot of what we'll do actually is referring to the specific group sizes. So N1 would be 53, N2 50, and N3 50. Yeah. Thanks, Suzanne. And the number of groups is K. So we have 3 groups here. So that's our K.
Is K only used in Anova?
Nope.
You see K, any place we see K, it's gonna refer to number of groups,
I don't want to say always, but
but pretty.
a lot of the
standard.
time, yeah.
Okay.
Yep. Okay. All right, let's run through one. So, analysis of variance is trying to tell us what? So tell us again, what's our null hypothesis for, actually, what's our alternative hypothesis
That there's
for an
a difference.
analysis of variance?
The
That
difference in the mean.
there's a difference in the means between the two groups, right? So in order to be able to say whether there's a difference in the means, we have to see how the data vary, right? Is there consistency, are things equal between the groups? So I'm going to say, we're going to have our 3 groups here, Utah, US, and international. And we're not talking about any specific outcome right now, but I'm just going to give some scores here. Let's say say each of these has a mean of 3 in the groups. And here you have 2, 3, 4. Here you have, let's see, 1, 3, 5. And here you have 3, 3, 3, right? So we do have variation in the data, right? So if we're taking all 9 data points here, so if our capital N is 9, we do have variation, right? What's our mean from this data? If we were to look at all 9 of these data points, well, we can add them all up. So we take 5, 9, 10, 15, 18, 27. So our mean is 27 here. This is, sorry, that's our sum. Divided by 3 would be 9, right?
27 divided
What am I doing?
27
Divided by 9, thank you. Yeah, that's 3. Okay, this is referred to in analysis of variance as our grand mean. Okay, this is the mean of the entire data set.
Is there a formulaic symbol for that, or is it just spelled out?
I think you sometimes see an X with 2 bars on it. Because an X with 1 bar is well, traditionally it's the sample mean, but here what we have would be X bar 1, right? So this would be x bar 1, x bar 2, x bar 3. Okay? And actually, you can see when we did this, that there's two ways of calculating the grand mean. So you can either do what we did, and sum all the values and then divide by the number of values, 9, which gets you 3, or you can take the mean of the group means, and that will also give you the grand mean. So it worked here. It'll work out, regardless of whether all three of these are equal to each other. So we see that there's variation. Well, so our grand mean is 3, and in here, in group 3, we actually don't have any variation from the grand mean, right? So there's no variation from the grand mean. There's no variation from the group mean either. But in these other two groups, we do have variation. But we know from our null hypothesis, just by looking at this, what would we conclude about our null hypothesis?
We would accept it.
We would accept it because we can see that the three groups have equal means here, right? In order to be able to reject the null hypothesis, we have to be able to say or to show that there are differences between the group means, right? And so basically the way we do that is to break down the different types of variation in the data, right? So there's two types of variation that we're concerned with. The first is the between group variation. The other is the within group variation, right? So I'm going to actually just adjust those real quick. Okay, so here we see some variation between groups. So on average, the grand mean is 3, right? And if we're looking at how much variation there is between groups, we have one group where there's no variation from the grand mean, right? We have another group where the distance from the grand mean is 2, right? So yeah, 3 minus 1 would be 2, and 5 minus 3 would be 2. Okay, so on average, those two groups are 2 points away from the grand mean. And let's look at within these. So here, the data points are only 1. So this data point's 0 away from the group mean, because now we're asking within the groups how much variation is there, right? Because this is the between group variation, this is the within group variation, right? So here, 0 is 1 point away, 1 unit away from 1. 1 is 0 away, and 2 is 1 away. So on average, they're slightly less than 1 away each, right? These ones are 2 away each. So it looks just by eyeballing this, it looks like there's more between group variation than there is within group variation. And in order to reject our null hypothesis, that's what we need basically. We need to see more variation between the groups than we see within the groups. Okay? So,
Say that again.
in order to reject the null hypothesis, we need to see more variation between the groups than we see within the groups.
Okay.
Okay? Because ultimately the way that we calculate our test statistic here is by comparing the variance between groups. So we take a ratio of the variance between groups over the variance within groups. Now this will be adjusted by degrees of freedom, but essentially that's what we're doing is we want, if there's no variation between the groups, right? So we can see this, the F is basically the between variation divided by the within variation. If there's no variation between, right, if these were all 3, there's no variation between the groups. So on top, our numerator here would be 0, and it doesn't matter how much within group variation there is, our F statistic is going to be 0, right? And we'll see that in a minute, the way we calculate our test statistics is basically the higher the F, the more likely it is to be significant. And the closer to 0, the bigger the p-value will be, right? So if there's no between group differences, our F is 0, we'll say it's not significant, and that makes sense because we can see that there's no differences between the groups, which is what our hypothesis was.
Okay, so you said that the closer that it gets is 0, and then the bigger our p-value will get, but wouldn't that show, oh no, they're right, never mind. So the smaller the p-value, that means it shows significance.
Yep.
Sorry. Okay.
Yep.
Assumptions.
Okay.
Before you move to that slide.
Yep.
On this example on the slide, what would the variance between groups, what is the actual number? Would it
So
be 1?
we'll go through an example of that.
Okay.
Because the way I did it here is actually a simplified version.
Right.
In order to do it, you take all 5, so you have 5 values within each group, and basically you say that on average, this group is 1 away from the overall mean, which is 4, right? So then for each observation, you basically take that 1, and so that variance is 1, so that is 1 away from the grand
From 5
grand
to
mean,
4.
and then you do that 5 times
Okay.
basically.
Okay.
We'll run through one of these together and you'll be able to see how it works out. But you basically square the difference from the grand mean, sum them all together, and that's what gives us the variance. So we'll see how that works. So this is the distribution that we use to calculate our p-values and to determine our critical values, okay? It's called an F distribution. It looks very similar to what we'll see in a bit, which is a chi-square distribution. We don't need to focus too much on the technicalities of this, but what do you notice here in terms of the shape of the distribution? It's skewed, right? It's skewed positive, and this isn't labeled here, but the y-axis would actually be 0 there. It's all positive. Why do you think it might be all positive?
Our alternative hypothesis is not equals, or does not equal, it's greater or lesser.
Well, according to that, then it could be less, yeah, it could be negative or
Greater,
positive.
So greater than, our alternative hypothesis says that treatment program is greater than the control.
Well, in this instance, we said they were just not equal to. And this is the distribution that you use regardless of whether it's a 1 or a 2-tailed test. Okay, any other guesses as to why all the values might be positive here?
I think the only, I can't remember the name of it now, but basically it's impossible to cut a negative length of wood. It's impossible to get negative numbers.
So it is impossible to get negative numbers for a specific reason. The way we calculate the F statistic is we square the differences, and so anything that's negative will be made positive, right? And so you can see that this looks kind of like a normal distribution that's been cut in half, right? It's slightly more leptokurtic than our normal distribution, right? It's slightly taller. Remember our platykurtic, leptokurtic?
Oh, okay.
It's slightly
So
taller.
is the apex there, would that, in our scenario, would that be 3? Because that's the mean?
So what we're looking at here is basically the distribution of F, right? So it's saying that the majority of the time what we're going to see is F values that are close to 0, okay? In essence, you can think about it like a normal distribution. And let's say that we were going to randomly choose a number from a normal distribution. So we have a normal distribution that's centered on 0, okay? And we have, 1, 1, 2, 2, or whatever, okay? And we were going to randomly choose a number from this distribution. How likely is it that we're going to get a number close to 0?
95, bro.
I mean, we don't have to be super specific, but we know that really the large share of the distribution is going to be
66%.
close to that mean, right? So it's kind of the same idea where now we're not considering anything below this point. I mean, we kind of look like this in the F distribution, right? It's a something similar to this. That's basically saying that a lot of our values are going to be close to 0, which means often what we'll see is similar group means, right? Because 0 means there's little between group variation here. So I don't want to get too caught up on this, but just to state that this is the distribution that we're using. And it's kind of like randomly select. It's like saying if we were just to randomly choose, it's more likely that we're going to get a lot more values close to 0. And that's basically what this is showing. Okay, so let's work through one together. So I'm going to change our group values here. We'll still call these our Utah, US, and international group. So here we have 3, 2, 1. We have 5, 3, 4, and 5, 6, 7.
Are we doing this just by hand or on SPS?
Yep, we're doing this by hand first, and then we'll check our work in SPSS. Okay, so the first step will be to calculate our grand mean. And we said there's 2 different ways of doing this, right? The first way was to do what?
Add them all together and divide them by the number of.
Yep. Yep, so take all these, sum them together, and then divide by 9. I actually got it here, but if you want to do it along with me, we can do that. So 3 plus 2 plus 1 plus 5 plus 3 plus 4 plus 5 plus 6 plus 7 all over 9 is 4. So our grand mean is 4. And we said, what was the other way to get this grand mean? To take the average of the 3 groups. We can see that it's 4 here, right? Because 4 is right in the middle. 1 is 3 away from 4. 7's 3 away from 4. And so 4 would be the average of those 3. Wait, sorry. Those weren't the means. Those were just the bottom values.
2, 4,
So we're 2, 4, and 6, but it still works out. So, yeah, our average of our group averages is 4 here. So, and that's what we've got. 2 plus 4 plus 6 divided by 3 is 4. So, now, to calculate our ANOVA, we need 3 things. So we need to calculate what's called the sum of squares.
I remember doing this now.
Do you?
By hand.
Okay, it's the sum of squared deviations. Okay? What do we mean by deviations? It's the distance of something from something else. Okay? So in this instance, we're calculating, well, let me just say first. So we have our sum of squares total, which gives us like the full amount of variation in all of the data across all 9 observations. Okay? We have the sum of squares within the groups, which tells us how much variation is within each of the groups on average, and how much variation is between the groups on average. Okay? And in order to get a significant result in our tests, what do we want here? What do we need to see? We want more between group variation. So the first step is to find out the total sum of squares within the model. So the way we do that is we take our grand mean. So our grand mean is 4. And then we look at how far every single observation is from that grand mean and square it. Okay? So we've got it here. Let's actually write these out on the board. So let's start with the Utah group. So we have 3 minus 4 squared, right? Plus 2 minus 4 squared plus 1 minus 4 squared. I'm going to go down a row to say we're on our next group now. So now we have 5 minus 4. Okay, remember we're doing the difference of every observation from the grand mean, or these would be deviations from the grand mean. Okay, so next we have 3 minus 4 squared plus 4 minus 4 squared plus another 5 minus 4 squared plus 6 minus 4 squared plus 7 minus 4 squared. Okay? So we can just look through those real quick and see we have a negative 1 here. Squared is 1, right? So do 1. A negative 2 squared is 4. Negative 3 squared is 9. Negative 1 squared is 1. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Okay? So let's sum these up. We've got 14, 15, 16, 26, 30. So this gives us our total sum of squares.
Johnny, does this test always have to assume that there are equal numbers of variables in each group?
Good question. The answer is no, but it can be problematic. When do you think it might be problematic if the group sizes are
Because the grand
different?
mean will be different from the individual group mean. If there are more, let's say there were 5 in group on 5,
Yeah.
the means, the grand mean will be different than the group.
So you're getting at why we test the assumption of homogeneity of variance, right? Remember, the first thing that we ask ourselves about the homogeneity is what?
The size.
Do the groups have equal sizes?
Right.
Right? So we wanted to know, is the n of the largest group equal basically to the n of the smallest group, right? This is where we take, so this is slightly different in Anova because we now have more than 2 groups. Before we were just comparing the size of the 2 groups. So this is the 1.5 rule, right? So if the largest group is more than 1.5 times the smallest group, then we get concerned about homogeneity of variance. If they're more similar in size, then we're okay. But the problem is, Mike, to answer your question, if the groups are different sizes and their variances are different, then that causes problems for the way we calculate this. So that's why we test for that assumption. So, okay, our next step then will be to calculate the sum of squares within the groups. Any guesses on how we might do that?
Take each number, compare it to the group mean,
Yep.
Compare it to 0.
The group mean. Okay, so we have each of our group means, right? So you take the first group, and for the first group, we're saying how far are those from the group mean of 2, right? So you have 3 minus 2 squared plus 2 minus 2 squared plus 1 minus 2 squared.
Okay.
Wait, isn't the group mean 4?
This is the group,
Oh, just
right?
like that.
For
version.
group
Oh, just
one.
for the group,
Oh,
Because
okay.
remember, this is within group
Okay.
variation. So we're saying how far is each one
From
in
the
this group
actual.
from this group mean?
Okay.
Okay, so I
Janie.
thought we said that the within group deviation was off of 0. So why are we looking at it based on 2 there? Did I
So
miss
what would an in-group variation of 0 mean?
I just thought that the deviation was
They all
off
be
of
They were all the
off
same
of
number.
0.
So 0 means, because a 0 variation means there's no variation. A variation of 0 would mean that if your group mean is 2, that all of the values within that group is 2, and their differences, breaking the tray here, I was leaning on it, that their differences from that group mean would be 0. Okay? So we want to test, this is within group variation from the group mean.
Okay.
Yep. Okay, so we take 3 minus 2, where we go? 3 minus 2 squared, 2 minus 2 squared, and 1 minus 2 squared. So what do we do for the second group?
5 minus 4 squared.
5 minus 4
3
squared.
minus 4 squared.
Yep.
So
Plus
how-
4 minus 4. Yep. Go ahead.
I'm just looking at forward. I'll keep going. I guess I'll ask at the end.
Okay, then here,
5 minus 6 squared.
5 minus 6. Yep. 6 minus 6 squared plus 7 minus 6 squared. Okay, Janie, how are you feeling? Are you still confused? Do we need to talk about it a different way?
I just remembered it differently, but I'm just gonna throw that piece out and go with this piece.
Okay.
It reminds me of when Sterling did our ages,
Uh-huh.
and did an average of our age, but within the group, the variance of age.
Mhm. Okay, so now we add these all up basically, right? So we have 1 squared is 1. We have 0 here. Negative 1 squared is 1. We have 1 squared, negative 1 squared, 0, negative 1 squared, 0, and 1 squared. So our total is 1, 2, 3, 4, 5, 6 for our within group sum of squares.
So this is like, well, how come if we're talking within the group, how come we're adding them all together?
Because it's saying this is the total variation within the group. You could ask what the average variation within the group is and divide, right? So here, the average variation within the group, so here you have a 1, a 0, and a 1.
Uh-huh.
So the total sum of squares is 2, and you could say that the average deviation of those within group observations are 0.66.
Would you list it as the N1 then, or
Okay.
however Suzanne said that? How would you list, it wouldn't be N1, but is there a way that you'd show that, like?
So this
SS1?
formula would be, is that what you're asking to
Yeah,
figure out
would be.
this? So this would be the sum of squares for group 1 divided by small n1.
Because there's 3.
But you don't need to know that
Okay.
typically, because the way we calculate the statistic is just with the total, where it's just summing all the squares together.
Okay,
Okay.
I guess if we're talking, I'm confused with the in-between groups. If we're talking just about that one specific variance between them.
So basically, this is what we're doing. We're saying, what we did first was we summed all of the differences from the grand mean to say, in the whole data set, this is the total amount of variation, right? Does that make sense?
Okay.
Not the average amount, this is the total amount of variation, okay? That every observation, this is how far they all were
From
from
the
the
mean.
grand mean. So the total
Oh, okay.
is 30, okay? Now what we're doing with the next steps is to divide this and to say how much of that total variation is between groups and how much of it is within groups.
Got it. Okay, that makes
Okay.
sense.
And actually, now that we've done this is sort of like having a degrees of freedom of 2, right? Because once we know the total sum of squares and another one of these, we actually can calculate the other one,
Right.
right? So if the total is 30 and the within is 6, then the between is going to be 24, okay? Although, let's check it and run it through together.
It's gonna be 30 minus 6.
So here's how we get the between group sum of squares. So we take, and this is what I was trying to explain before, but it was a little difficult to do. So we take the average from the group. So the group 1 mean is 2, right? And we want to know how far that is from our grand mean of 4. It's 2 away, right? So for the group, we do 2 minus 4 and square that. The key is we have to do this once for every observation in that group. Okay?
Why is that?
Do it 3 times.
Just how you do it.
Just how you do it, okay. All right.
Yeah.
It's just how the computer does it, right?
It's trying to account for what Mike was addressing in that you might have different sized groups, right? Because if you knew for sure that all the groups were the same size, you actually wouldn't have to do it. You wouldn't have to add them all up.
Because if you had in Utah 2 more that were each 2, you'd still have, Utah would be average at 2, but you would, would it throw everything else off, right?
Yeah, exactly.
Our sum of squares
So-
would be bigger, wouldn't it?
So if there were 5 observations here, yeah, it would mess that up.
Okay. That makes
This
more
is
sense.
assuming, well, I guess this doesn't assume that the way we add it together here doesn't assume equal group numbers. You know, if you were just to say, I'm just gonna take the difference here, you know, do this once, 2 minus 4, 4 minus 4 for the second group, and 6 minus 4 for the third group, right? And assume kind of times it by 3. And actually, if the groups are the same size, you can do it that way. But if they're not, then it'll mess you up. Okay. So it's easier as we write it out, just to show that for each observation in that group, we show how far that group is from the grand mean.
Algebra comes in useful in this, huh?
Yeah. Okay, so here you got 4
Yeah,
minus
this is
4.
good.
I'm not going to write these out because these are 0. So 6 minus 4 squared, 6 minus 4 squared, and 6 minus 4 squared. Okay, so here we get 2 squared, so 4, 4, and 4. These are all 0. Here again we have 2 squared, 4, so 4, 4, 4. Okay, what's 4 times 12? 24. Nope, sorry. I don't have 12 fours, I have 6 fours. Okay, 24. So same as what we figured out by taking the total sum of squares minus the within sum of squares. Okay, so again, what we're doing is we're showing how much total variation there is in the data, and we're saying how much of that variation is between the groups and how much of that is within each of the groups. Okay?
That makes sense.
That's the basics of the Anova test. Okay? So the next thing that we need is to calculate our degrees of freedom. So I mentioned yesterday that Anova is one test where we actually have 2 different degrees of freedom. So we need one for, so back to here real quick. I mentioned that this is the basic calculation of F, right? It's the between variation divided by the within variation, which gives us the share of all the variation that's between the groups. Okay, but we have to adjust these for degrees of freedom. So basically we have a degrees of freedom for the between and a degrees of freedom for the within. So here's how you calculate the 2. So the between is in our numerator. So you'll see this notation sometimes. Degrees of freedom for the numerator is k minus 1, and our k is what? Again, that's our group, the number of groups. Okay, so the degrees of freedom here is 2. And then for the denominator, oh, I need to change that one also. We have the capital N, which is what?
The amount of
The total
observations.
number, which is 9 here, right? Minus the number of groups, which is 3. So our degrees of freedom here is 6. Okay?
Just curious who thought all this up?
Yeah. A few guys did a lot of this stuff together.
Like
We
those
have-
guys that
we
sit
were
on the
talking
giant
about that last
chalkboards and
night.
they start at the top
Yeah,
and
talk about geeking out.
Well, I think it was like the golden age of academia where guys just like sat in their offices all day and did nothing but just like do
Dream up
this
stuff
stuff.
that they got
They
named.
didn't have to teach, they didn't have to do anything other than just read books and, yeah.
And they just proved this.
Yeah, yep. So, well, and people, and imagine, right, if you guys were doing dissertations 30 years ago, you'd be doing all of this by hand, always, right? There was no SPSS, there were no computers that could handle this stuff. Right? I wouldn't.
And I'm sure you wouldn't either, even though you would
Yeah.
enjoy it.
Isn't that why all that time ago, education educational leaders probably did not get this kind of training. They did not go to this.
Oh, I'm sure,
And I
yeah.
think you just explained why there was such a exponential increase in the number of research projects in education after year 2000 with the advent of the internet and online software. Made all this stuff easier. I can see why nobody would do that before.
That's true. Yeah.
Torture.
That's software came out, yeah.
And that's why
Okay. So-
education has come late to this.
So we use our degrees of freedom to find out what our critical value is, right? We've got a handy table like we always do. That's of course different than all the other tables we've used, okay? So we have here the degrees of freedom for our numerator, right? So that's 2. And then our degrees of freedom for our denominator is 6. So our critical value here is 5.14. Okay. Actually, we haven't even calculated what our test statistic is, which will be our F, but we will do that now. So the way to get the test statistic is to take your sum of squares between, so that's our 24. So I'm going to do this here. 24, and divide it by its degrees of freedom, which is 2. And take that over the within sum of squares, which is 6, and divide it by its degrees of freedom, which is 6. So here we get 12 over 1, or 12 for our observed value. Okay, and here, right, what were the cases, the tests that we're looking for values smaller than our critical value? Yesterday, which ones did we cover? Remember, there were 2 tests that we wanted to find an observed value smaller than our critical value for it to be significant.
It was the funny name one, the Wilcoxon, right?
Yep, so the Wilcoxon and the Mann-Whitney U. So those 2 non-parametric tests, we look for observed values below our critical value. But for all of the parametric tests we've covered so far, we're looking for observed values that are higher than our critical value. So that's what we have in this case. So what would we conclude here?
That we,
Wait, so this one you said was expert.
so we reject the null hypothesis.
Yep.
But we don't know which group.
Great point, Janie. So we do know now, so what the table is showing us, you can barely read it here, but this is for alpha levels of 0.05, right? So all we know is that p is less than 0.05. We don't get an exact p value from these tables, right? We just know that it's significant. But Janie just raised an important point. So we now know that there's a difference between the groups, but what don't we know? Which groups, right?
Right.
Although by looking at it, I mean, the differences are all equal, right? So they're probably all different from each other. But the next part would be to conduct the post hoc test. But let's do this first. I want to check our work in SPSS.
Okay, so this is greater than, and so we would not reject the whole null hypothesis.
So we would reject.
Reject, because it's greater than.
So let's summarize
It's
real
not
fast.
non-parametric.
This
It's
preposition in the language that
Well,
we're
and I want to be careful not to make that distinction because some of the non-parametric tests do it the other way.
Okay, so it's not.
So far, we want the observed to be greater than the critical.
You should make a chart for this one.
Yeah, that's a good idea, actually.
Yeah, that would be great to have this.
Although, essentially it doesn't matter because you guys are never going to be doing these by hand, right? This is just to show you how it works,
But
and
it'd be
then
good-
Yeah, but
we're always
don't
going to
we-
do it in
But
SPSS.
don't we
we'll
need
still
to-
have to look to see if the critical value is more to determine, right?
Nope, because all SPSS will give you the p-value. And so you just, the p-values don't change, right? For all of these tests, we want the p to be less than
Oh, because
0.05.
it just calculates the intelligence, whether the
Yeah.
p-value, so we always want the p-value less, but in our.
For the test, right? In which situations do we want p to be above
When it's
0.05?
the
The
variability.
For the assumptions, for testing our assumptions.
I get it now, so the critical value would be 5.14, which means 12 is so much greater than that, it'd be further to the right, and we're doing a race.
Yeah,
As test speed to the right.
yep. Okay, let's check our work. So everyone open up SPSS. And open up a new blank data set.
Doesn't matter what view, data or variable.
Start with the variable view.
Okay.
Well, actually, let me ask you guys first.
That's true.
How, well, let me get this ready. Okay, so here's our data. How would we enter this into SPSS?
First we have to name it, so we would go to variable view, and so
Okay.
group one,
Group
group two, group
Would have
three.
a group would be a 0, 1, 2, do you give each one a number?
So, yep.
Is that in transform?
So you have to, well, you can just, because there's so few variables here, we're just going to input it manually.
We're just doing a new one. we're calling
So, but what
it,
Cami was saying, we first want to create a variable called group,
Okay, you just.
right? So go to your variable view. You can just type in under name here, group. So let's see if we need to change anything. It lists it as a scale measure, so we want to change it from a scale to what?
Ordinal?
Is it ordinal?
What is it? 1, 2?
Group 1, group 2, group 3.
Oh, categorical.
Yeah, so that's nominal here in SPSS. Okay, and the other, so for our outcome, I'm just going to name it something like score. Okay, and that one, we want the measure to be scale, right? Scale, remember scale in SPSS is for anything continuous, so that's either ratio or interval data. Is everyone with me to this point?
No, mine's installing
No,
this.
because I was thinking we had to have
Did yours do
one for
that?
each group, but we
Shut
don't.
down on
Just group.
Correct, yeah. So we want one variable that is group, and then we'll have different values to say which group they are.
Yes, sorry.
Two variables.
So now, once you've done that, you can go to your data view
You put in group.
and put in the group. So for group, I'm just gonna have 3 1s for group 1, 3 2s for group 2, and 3 3s for group 3.
To measure
And then I'll put in the scores. So the group 1 scores were 3 2 1, 5 3 4 for the next group, and 5 6 7 for the third group.
That's another one of you're gonna put in score, sorry, you're gonna put in the name score. And then when it autofills, you're gonna put 0 and turn this into a scale. So that measure.
Okay.
That measure of
Yeah.
needs to be
Okay, so when we
nominal.
in these huge data
And
sets,
this one is scale.
what, do we have to do
Then
this by
we go back
hand?
to
Do we have to,
data.
or can we like export them using CDS files?
Yep, you can.
Okay.
Mhm.
Or Excel?
You can go straight from Excel, you can use CSV, you can use all kinds of
But
stuff.
now I'm confused.
Yeah, Qualtrics makes these life easy.
Yeah,
Oh, okay.
Janie, go ahead.
I'm just confused where we get the score from.
So this is from our, just the slide
Okay,
data
so
here.
we're saying, okay,
So
I get it,
group
I get it.
1,
So
3
we're-
2 1.
Group 1, 2, and 3 do not have their own column. They just have their own section within the column with 1, 2, and 3 as an indicator of which group they're in. Got
Yeah,
it.
because remember what,
That's what I was confused about to ask, yeah.
and that's why I go through this, because it looks different here than it
This
does.
looks like an Excel
Here.
spreadsheet, and this is not.
Exactly.
And you have to
Yeah.
Give yourself all of your slots and then you enter the spreadsheet.
Right?
So
This,
last night was valuable, now, because now last night even makes more sense. I mean,
Good.
This helps me understand last.
Yeah, last night
Yeah.
I was just plugging in numbers, I didn't know where I was going, but now I get this.
yeah, because remember, this is showing us, whoops, this is showing us what variables we're comparing, right? Because we know that for an ANOVA, we're comparing one independent variable that has multiple groups we're comparing the outcome variable across those. So we're dealing with two variables, so that's the way we put it into
So
SPSS.
regardless of the number of groups you have, you're only gonna have one column, but that group, that column is going to be differentiated by 1, 2, 3, 4, 5, 6.
Correct. Yep. Okay. So is everyone with me now? Okay, let's check it. We're going to run this. We're going to ignore our assumptions for now. Let's go to Analyze, Compare Means, and then it's at the very bottom, One-Way ANOVA. Okay, the 1 for one-way means we have one independent variable.
Okay, and our dependent.
So what would go in our dependent list box? The score.
Is there-
Because that's what's dependent.
Sorry, maybe it would help you helpful for others, but it'd be a specialty for me. Can you conceptualize this for us? Like, what kind of groups, like, can you put it in terms of either sports or something like that where we can see, understand? Yeah, baseball teams,
Sure.
hitters,
Okay.
basketball teams, whatever, quilting, I don't care what it is. I just need to conceptualize something.
Okay,
So
yeah,
I know what I'm doing.
I do have an example.
Or just call it.
To run through. Let's do this first. Let's do this first, because this is just checking our work here.
Okay.
So we're just going to see if we got the results right, and then we'll have a more conceptual example. Okay, so we'll put score here, because yeah, I totally understand. You have this just a dependent name score. It's like hard to even know what's going on there. Okay, so score, group, we'll go down in the factor. Okay,
Does it matter?
Yes,
It does,
because the score is the
Score is
thing that's
dependent
gonna
on
change.
the group.
yeah, it
Score is
does
dependent.
matter.
Score's the thing that's gonna change.
We're not
The
doing
group
anything
is
else right
a
now.
Random assignment could be. Right.
Okay, let's just hit OK and run it. Okay, so let's look at the output.
So we don't do anything to the,
No other options right now. Okay, so here's what it produces. It gives us the table. Okay, it tells us the sum of squares, these three that we had. So we have the sum of squares between 24, the sum of squares within 6, and then the total is 30. Okay, we have our degrees of freedom for the between 2, the degrees of freedom within 6, and then the total is 8, which we didn't do, but and then we have our F statistic, which is 12, and our p-value, because we were using the table, all we knew was it less than 0.05, and here we get the exact one, it's 0.008. Okay?
And you record that less than 0.00.
Actually, if it shows like this, list the exact thing. Say p is equal to 0.008. Only when it shows as 0.000, then you say it's less than
I get it.
whatever. Yeah,
Because we don't know. It's
exactly.
Did we calculate the mean square within groups, the 1.000?
Nope.
Okay,
We
and is that important?
It's basically the square. Wait, hold on. Is it the square? Hold on. Mean square error. No, I mean we won't need that. It's like the standard error of that sum of squares.
Okay.
Did you click anything statistics wise to get that table?
Nope.
Because I'm just getting a rejecting the null.
Are you?
I'm not getting that.
Let me see.
Just got the upgraded version that just tells you what you should do.
And obviously I don't.
Before you just talk to it.
I think Anthony, or no, Mike
No,
got it.
Suzanne got it.
Suzanne got it?
That's not a light package, right?
It's not.
Well, Susanna knows Susanna.
She's like, I tried and Suzanne's like, I got this.
Suzanne's like, we'll take care of it for you.
For like the fourth or
We are
fifth, that was
equal
probably the first thing you wanted.
opportunity in this group.
We have
Yeah.
to
Okay, go back up. analyze.
Yes, we are, and
Oh, I
it's
know.
been really good, so I would
It's okay,
just
this is
go
all
back
math.
and watch.
It's all the math stuff.
And one way Anova.
We gotta mix it up, because some
It
really,
really
I went to do
Yeah.
for another year and a half for a PowerPoint, I started with part out, but it's like, I don't even do it.
Well, I found it yesterday, those two.
Yeah, that's, I mean, I just always highlight.
It's like.
To know you're saying how they come
But
about
I
it.
thought it's enough.
I think that's really insightful. I think, yeah, so that's what I'm saying,
Well, both ways, I think it's insightful as
You know,
well. We choose
to make sure I know how to-
right.
continue to do it.
I mean, it's good background to understand
Yeah.
things, but I'm gonna put that in.
So you have those two areas.
Okay, come on, let's PSS.
Don't your lungs burn?
A slow.
An hour to do what?
Well. I can go out for
There's no
Singing on a license.
Before you read.
That was my 2-week thing. Did you have to upgrade? Did you have to do something when you, with the crash the other day?
Mine does
I
that.
had to reinstall.
Mine does that it constantly asks you for an upgrade.
And the other thing I did
The
was,
license?
so I sent in my student ID to make
Yeah.
sure they got it.
Okay, so.
And I don't know if that mattered or not, but then I just reinstalled it and I put it right on my desktop. Not on my launcher, I put it on my desktop. That's.
So that's why that's too bad.
I have a
Okay.
problem.
Okay. So let's fulfill Mike's request and go through an example that we can actually make sense of. Let's see. Let me share this first. Oh wait, we talked about this yesterday, right?
Yeah, but.
Okay.
Yeah.
But we talked about it in the
In a
context of a
different-
t-test, not in this context. So here for the Anova, now we have all of our assumptions. So we start with the sample sizes, right? Now we're looking at all the individual groups. And actually the notation is wrong on here. These should be little n's. Okay,
Why is it the K, like if there's more groups than 30?
so K,
The number of
this type of notation, yeah, is just saying however number of groups you
Oh, okay.
have.
Like two individuals.
Yeah, yep. Okay, so then we check the normality assumptions the same way we've always done. We check the homogeneity of variance. And then we run the test. One difference here, okay, with the t-test, remember if the homogeneity of variance was violated, what do?
Go drop down.
We stop, drop, and roll, right? The Anova doesn't give us that output automatically, that bottom row to interpret. What that row is Welch's correction. In the Anova, we have to tell it to also provide us those results if we want them. So,
And do we just always want them?
well, from what I told, I think most of you were in the room yesterday when we talked about this, and I told you that some researchers make the argument that you should just always use Welch's correction, which means don't even worry about, like, some people don't even assess the homogeneity of variance. Well, sometimes they do, but even if it's equal, they just use that corrected version. So they stop, drop, and roll no matter what. It's the more conservative one. It's going to reduce your likelihood of type 1 errors. It will also sometimes make it so that you might get a non-significant result because the p-values will be slightly larger for that.
Do you have to make that decision before you run your tests, if you're going to
Yeah, you
use
should.
Welch's or not?
You should, yeah. Yeah, so the answer is yes. If you wanted to just be safe, you could just use Welch's every time and just have that be kind of the standard. Okay,
But in Anova, you have to ask it to run a Welch's.
yep, and I'll show
then
you
just had to do it.
how to do that. So we've been working with the NAILS data set. We can go through that, or I could pull up a sports one for you, Mike. We could run something fun together.
Quilting's fine with me.
Okay.
I just want to put something real to it.
Tangible.
Yeah.
So there is a data set in the content page I will warn you, it's large. So here we have this MLB StatCast data set.
Where'd
Okay.
you get this from?
So this was my son's science fair project for this year. Okay, we got first place.
We.
I just said we.
What school does he go to? Because I don't want to compete against that now.
He's in third grade, so they just stay at the school. They don't go to any of the bigger stuff. Yeah, it's this MLB StatCast one. It'll take a little bit to download.
Holy cow, you're not kidding.
Yeah, it's big.
And then it's done.
Okay, now we're talking.
Can't believe it. Use SPSS for kids to like to go.
Would like to.
Just all of a sudden the light bulbs come on.
Does your son understand SPSS?
No.
Yeah.
I mean, he can't do it himself. I talked him through the results. I ran some regressions for him. And I'll show you guys. I'll show you guys
How old is this
when we get to
child?
regression. He's 8.
Yeah.
That's great.
Oh my God.
Yeah, he tested. So his question was, how far do what's the impact of elevation, humidity, and temperature on how far baseballs fly? Pretty much.
Yeah, because in
Yeah, it's
Denver,
fun.
you're gonna hit more taters than you will in.
So I can tell you exactly how much farther they're going to go in Denver
Really?
than elsewhere. Yeah.
I like golfing in Park City better than I do in.
Yeah.
Where did you get it though?
So I searched around online. This is publicly available data.
His son searched around.
So,
Gave it to dad.
so let me tell you what this is. So StatCast is something that Major League Baseball introduced a few years ago. So we actually toured Coors Field last fall, went through the stadium, and they have these white little sensor things all over the whole stadium that are constantly recording data. And so in the data set here, what you have is a single hit, a single ball that was hit. This has every single fly ball and line drive that was hit in Major League Baseball in 2008.
Wow.
You can download every single pitch if you want to. It's crazy. But yeah, so here we have, it's all fly balls and line drives, and you can see what the data are. So you have the distance that the ball traveled. You have the speed at which the ball came off the bat. That's launch speed. You have the angle at which the ball came off the bat. I inputted, so we added some things to the data set because it didn't have the elevation that we wanted to look at. So, but this one has an elevation variable in. You have the speed at which the ball was released from the pitcher's hand. I mean, all kinds of stuff. Okay? And then you've got, the fun stuff is, if you scroll over, here you have the player names. So you can see that Howie Kendrick hit this first one. Here's what I want to know. Okay, I'm going to come up with a question real quick.
Could you put in like all the, okay, was it a data set that like?
This data set
Flies out to center field or injured,
that was all there.
that was all there?
Yep.
Okay.
He didn't do it, he just downloaded it.
I just downloaded it. I did add elevation. Okay, so we went and found the elevation of all the cities. I also,
Wow.
Okay, the hard part was getting the temperature and the humidity data. Because my wife was really mad at me because I was spending so much time on it. I was at home for like 2 straight work days, like doing this.
I have a new respect for that.
Certainly, you turn this into a publication.
But look, now I'm using it in class, right? So,
Well, then you should have done it, yeah.
so yeah, maybe I will start publishing some stuff.
I'm like, Mike's one of those parents that does these.
He's the problem. I know,
But I'm not like that with most
I'm
stuff.
the ones that lag behind that can't compete.
Yeah.
You're big.
Yeah, so for the temperature and the humidity, we went for every city, month by month, what their average humidity and temperature are, and then added that in. So
Wow, it's a lot of work.
I never realized how many coastal cities the games are. Like hardly any of them have high,
yeah, it's true.
high elevations.
So, man, you guys could really pull me off from topic right now.
He wants to go there so bad. Tell us more.
We'll use this
Is the
more.
VES one, is that the destination?
So where is that?
This is going on YouTube.
There's one that's not only does it have the player's name, but it looks like it's like what happened to the ball.
So do they have home
Yeah,
runs?
yep.
Oh my
Say, like-
gosh, that's
So here, Howie Kendrick doubles on a fly ball to center, fielder, Ender Enciarte, Bryce Harper scores, Ryan Zimmerman to third. Yeah, it's like literally everything
But that
that
was
happened
the-
on that hit.
Yeah.
Yeah. So you've got where it was played. You have, they have different hit locations, so the fields, oh, this must be center, left, and right field.
You could do so
Right.
much with this data.
So
Left
7, 8,
to the
9,
fielder,
center, left, center, right.
This is really cool.
Okay. You have whether it was a ball or a strike.
No, that's the count, isn't
Yep, you have what the count was at the time. You have,
Is this the prep work before when you strike too big and beat your own team?
I don't know.
Is this the next level of Moneyball?
running regression.
Well, this is the money, this is what all the MLB teams are now using this stuff on a day-to-day basis. And not paying Bryce Harper because they can now think they can construct all the hits they need. All right, so we need to come up with a question, right? So a question that's comparing some type of groups.
I suck into it, like
Do you want to do elevation and home runs?
Sure.
Okay. So we have,
Or right-handed?
so we're gonna have, let's try to limit it. Let's compare Denver to, so the lowest elevation city is Philadelphia.
Really, it's lower than San Diego?
Yep. Here, we can look at them real fast. You guys are doing this on purpose. I know what you're doing. Okay. So let's look at a chart first.
it? Oh, yeah, we can look at the chart, yeah.
Okay, so
Say
how,
what?
How'd you get to that?
So we're gonna do
graphs, chart builder, right?
bar chart, I think is what we
Before you
want.
see the dialogue, what?
Sorry, am I skipping too fast? You
Yeah.
guys with me?
I got a
Okay.
dialogue box.
So that's.
Graphs, chart builder.
Okay,
Okay.
they just took me to a
I'm
dialogue.
gonna drag a bar chart up, and then we're gonna look at, we're just gonna look at the elevation.
And which,
In thousands or elevation, there's two, elevation in thousands or just. elevation?
The first elevation, the full one. Okay, so drag that to the y-axis.
Y-axis.
That's good.
Wait,
Mean elevation.
is that right?
And what are we doing, distance? Or?
Wait, we don't want a bar chart.
Yeah, I thought we did because we want to know location. Where
But that's gonna tell us the number.
Wait,
want-
Hold on, let me-
cities on the other one?
We want that. Yeah.
Cities on the.
So on the
Hold
one.
on, let me
yeah,
see.
we
Where did
want
you
to
find
see-
cities? I don't know. I just guessing. I don't think it's in there. I bet it's in there.
Yeah, because that's gonna tell us, hold on.
Hit location? No.
I think we want just descriptives.
Stadium location.
Where is it?
Say what?
How far down?
I'm just gonna run the,
I'm trying.
nope. I'm gonna do frequencies real quick. Frequencies will show us the just different elevations, although it's not gonna show us which one's which. But
Yeah,
you
if
have,
There's one that's
Stadium location.
stadium location.
So then can you do spell state?
Oh, yeah.
It's on the-
Stadium
that-
location and
on
then
the-
mean elevation?
Yep,
See?
that's what I did.
so you did a bar chart.
So
Yes.
high. Boston is low. Since all
Okay.
those towns
Philadelphia
low.
is the lowest. Boston
Okay,
and
there it
Philadelphia.
goes.
Can you see the whole thing though?
Stadium
Yeah.
location, mean elevation, yeah.
But there's tons of cities
Yeah,
that only
wow,
shows you
that's
three,
all right.
right?
No, that's 32
So then you
teams.
have to see
Where's
more.
stadium?
You, I guess I had to open it
No,
up.
where's
It's
stadium location?
Okay, I see.
Yeah.
Oakland
It's
is
farther
low,
down.
New York, what's NYM?
So you put that on the
Mets.
X?
New York Mets.
What's MIA?
How
Miami.
did you get
Oh,
to that?
Miami's really low.
How did you
Oh,
get to that
Boston.
view?
I just
Yeah, where is that stadium
Did
location?
you put the stadium location on the X?
It's hard to see those.
Is, how far down is the?
So mean
Oh,
elevation.
it's almost.
It's pretty far, yeah. It's hard to see the really low
And
ones
then just
though.
okay.
Boston looks like it's.
Colorado's just like
Yeah,
far heads in.
MIA is
going without any color at all.
San Diego, SD.
They have so when they mean high elevation, I mean, they're not kidding pictures to go there.
Wow,
Because
Colorado
they're
is.
gonna get
Man,
lit.
I'm not seeing that
Yeah,
stadium.
I was gonna say Colorado's.
Yeah, it's lower.
I didn't realize it was that.
Keep going.
Well, it looks like, is it
It's
before all the
under-
individual
It's
teams?
after,
It's
it's
after.
after.
Pitchers don't wanna pitch for Colorado.
Right, because their average, their hit
Yeah,
on
keep going,
average
keep
is
going.
just gonna be really bad.
Location.
Yep, location.
Okay.
I remember, I grew up in Colorado, you'd always see elevation signs, and then I remember
There we
going
go.
to
Thank
California
you.
and saw an elevation sign that said like
Yeah,
7. I was
so-
like, what, is that right? So I was gonna see like 4,000.
You should be able to order these too.
What, 7, is that, what is it?
So if you double click, let's see how we can sort.
Oh, really?
Yeah.
Oh, I can see.
Death Valley is actually
How would
lower
you do
than
that?
Cedar.
Oh, yeah, so you double click on it, then you can edit it,
What do you double click on?
the chart, then you can edit it.
I'm gonna try to, I'm seeing if
Oh,
we
like
can
lowest to
sort.
highest?
Yeah.
Oh, that would be good.
All these icons, you don't know what to do. Rescale. So what do you say? Oh, okay.
Can you do that when you
Maybe,
create the
maybe we
chart?
can't. I made all the charts in Excel.
They're
I
in
wonder
alphabetical
when
order.
you create the chart, if
Yeah,
there's
they
an
are in
option to do
alpha.
that.
Yeah.
All
All right. So let's compare. So we're gonna compare Denver. Yeah, Philadelphia is the lowest. Do you want to do? Let's do one kind of in the middle. Let's do Arizona.
Okay.
Actually, if you throw out Colorado, I mean, that's really an outlier.
Yeah. Yep.
The middle ones are really more like Cleveland, Cincinnati, Detroit.
Minnesota, Atlanta.
So when we get to regression, we'll use this data. I'll show you the models that we used to show exactly how much farther a ball will go in Denver, holding everything else constant. It's really interesting, actually. And there was one surprising thing. The effect of humidity was different than we thought it would be.
Go higher.
So humidity, it travels farther with higher humidity.
Oh, interesting.
Right, because the denser
Because when there's more water molecules, basically the water molecules displace oxygen and nitrogen molecules, which are heavier, and so it's easier for the ball to travel through water than it is in oxygen and nitrogen when there's less humidity.
So the best place to pitch is Philadelphia because it's humid in the summer and it's low elevation.
You don't want humid.
You don't
Oh,
want.
you don't want humid.
Arizona.
Well,
Arizona's high.
I mean, the question of pitching is different too,
than hitting.
because the pitching also is affected by these things, right? Because pitchers will throw slightly faster in Colorado, but also the ball doesn't break as far in Colorado for curveballs and sliders and things like that.
I just
So
don't,
then-
Colorado has a hard time signing marquee pitchers because nobody wants to come and pitch 81 of their games in that kind of.
Yeah,
But
So
you all the
you could
hitters wanna
do
go
home
there?
runs in cities.
Do you
Now
have,
if we know.
yeah.
Runs per
Right.
game.
do you have the distance from home plate to the fence of all these?
That's a good question. I don't know if it's in there or not.
Because they're just saying.
Now you're giving him a project.
I'm done with this. This is it. Okay, so let's see how much farther let's see if balls go farther in Denver, Philadelphia, or Arizona. Okay, we have to do some things to the data set because there are a lot more cities in here. So we're gonna have to restrict the data set to these 3 groups, right? So do you guys remember how we do that?
Go to data.
I don't.
Don't we go to data?
Select
Yes.
cases.
So,
Under what?
yep, so select cases. I'm gonna first,
Data.
Sort cases.
so data,
Data.
select cases, and then if
know that.
condition is satisfied.
Is it select cases or sort cases?
Select cases.
Yeah, I don't see select.
It's down at the bottom.
It's down
Oh, I
to,
see.
yeah, okay.
What's if condition?
Then I'm gonna hit if condition is
Oh,
satisfied and
right,
go in
and
here.
or Philly.
Okay? now we have to say we're focusing just on these few places or these few teams. And what we want is, where is it?
Okay, how
Home
did you get
team.
to that if condition? I mean.
So are you in select cases?
Yeah.
Then if condition is satisfied, click on this if button.
Oh, okay. So that one.
Then find the indoor stadium,
Oh, and click the home team.
click that over.
Oh, indoor stadium.
So we're gonna do the indoor stadium is equal to, and where these are, they're strings, it's text, right? So we have, these are the three we have. COL, they're all capital. I can't remember if Philadelphia is like that. Arizona is ARI. So when you have text in your variable rather than a value, you put them in quotes, okay? So you have indoor stadium is equal to quotation mark, capital COL,
Wait, go down.
and close that quotation mark.
And then.
I'm just gonna test that real fast to see.
It's, up
Hold on.
home team, above home team. It's.
Wait, don't you want location on that?
Doesn't work.
Isn't that what we're trying to do?
Oh yeah, I chose the wrong one. Sorry.
Is it spacey? I didn't want to correct you.
It was home team, I think.
Home team, we're gonna change it.
Oh, is there? Oh, no, no, location, location is also
Stadium
good.
location.
Okay.
Location?
Yeah, location.
Not in location, state, just location, right?
Just
Yeah.
Okay,
location.
hold on.
Stadium
Let me
location.
see if this works
Toward the very,
without.
very, very bottom.
Okay.
Here. Okay, actually you take the quotes off. I'm mixing up my stats programs. It's a different one where you use
So
quotes.
it's stadium location now?
Yeah,
Equals
okay.
Colorado.
So equals Colorado.
No quotes.
Now, we're gonna do a more complicated one, because it can be Colorado or Philadelphia or Arizona, right? So, all right, we're testing my SPSS knowledge here. I think this straight line here is used as an OR command. Okay? So,
Type of straight line.
it's a straight line, it's right here, next to the and percent.
And then you have to put a space.
So you do not have to. So the next one would be ARI,
What's the straight line mean?
or. I think it does. Again, I use a different program more than I use SPSS, so some things I'm a little rusty on. Stata. It's a code-based.
But this will be better for us because
Software.
it's not code-based.
Yeah.
And the textbook's written on this.
Are there spaces between all those?
No.
There don't have to be. There can be.
Okay.
Okay, and then we get continue.
PHI.
Okay, I'm just gonna correct to make sure I did it right. I'm gonna run the frequencies on that location variable.
Do you hit continue after? You get
I haven't yet.
Okay. I didn't get Colorado for some reason. Maybe I listed, maybe that's Denver? When we made the chart before, oh, it's COL, why didn't that work?
It worked for me.
Did it?
Yeah. I just have to, I can't remember how to group them now.
Did you put a?
Yeah, take out the space.
Oh, I don't feel comfy.
I'll try it again. Did you do your descriptives afterwards?
No, I didn't.
Run your descriptives and see if it worked. Hold on, I'm gonna take that off real fast.
Frequencies, right? It worked for you? Did you go ARI, COL?
No, I'm gonna run the thing right now. Oh yeah, COL didn't work. ARI and
Mine is
PHI
not
did.
running at all.
Check that.
Well, I'm gonna wait till.
Okay, let's do this.
Lost.
Let's forget about the holding it to these. We're gonna compare all 30.
Yeah.
Okay.
Okay?
Just
We
like
have a
this
huge
location.
we have a huge sample size. The thing where it's gonna get tricky is in testing our assumptions. So,
Go back and.
Go back and take off your select cases.
How do we do that again?
So go back in and have all cases selected. just gonna run this again
Okay.
fast.
Yeah, I don't know why it's not doing that.
All right, and now you just did.
Yeah, that's
did you
weird,
just
because it's in there as
do-
COL,
what
it
did
should
you
be
just do?
working.
Say that
Um,
again.
don't worry about that. Okay, this is what we're gonna do. We're gonna run. Let's just look at what the assumptions look like. It's gonna be crazy because we have a ton of groups. Okay, so go to explore and
Was that under?
just analyze descriptive statistics, explore. Okay, we're gonna put hit distance in the dependent list, and then the location in the factor list.
Stadium location or just location?
Mine is just location. I think
It says stadium location.
you guys have the value or the labels showing instead of the variable names.
And then,
In the factor?
Okay,
Yes.
in factor. Then in statistics, we're just nothing in statistics. In plots, we want histogram, normality plots with tests, and untransformed for Levine's test. Okay?
So for plots,
lots we want.
what was it again?
We want the histogram, the normality plots with tests, and the untransformed Levine's. Okay? It's gonna take a while to run. I didn't show you guys this, but you can see there are 60,000 observations, right? So there were 60,000 fly balls and line drives hit in Major League Baseball last year. We're looking at all of them.
So,
Okay,
Wow.
what does it say?
it
Oh, there it
just
is.
stuck out of one way.
It's probably
Oh,
just,
it just
it's
takes-
just taking a
it
minute,
takes a
yeah.
minute. Oh, yeah, it's super long though.
Oh, okay. This is part of the case processing summary?
Yes.
Yes.
Okay.
Okay, so you can see that there are about 2,000 or so for each location, right?
Number of hits.
That's the number of hits, yep.
Okay.
There's some missing data for all of them, but it's minimal. So let's go down and look at let's scroll past the descriptives for now. Let's look at the histograms. Histograms look decent, right? A lot of them look close to normal. Now there's tons of them because it's one for every different stadium. The Dodgers are very symmetric.
Where's Colorado?
Okay, let's get down past the histograms. The QQ plots, some of them are okay. Yeah, it's just kind of a pain to work with so many different groups, but it's all right. It's fun to see. The stem and leaves look good, or the box and whiskers.
Boston Whiskers look
You got
really
it with just the
good.
three?
Yeah, I just kept the three. It must have
Do we ever worry about
Oh, yeah.
distended? Normally
No.
we just took, okay, fine. That freaked me out.
Remember,
It's
I
probably
changed
sad.
it over here. then I went
Okay.
and analyzed, and just kept that.
Let's look at the test results. Okay, normality, we know is not going to be a problem. Why is that?
Because you have a sample of more.
Because all the samples are really big, right? If we were to be concerned with normality, look at the results. All the KS tests, they are all extremely significant, okay? That is likely due, at least in part, to the fact that the sample sizes are so big that it's really easy to get significant results. But again, it doesn't matter here, but the homogeneity of variance is significant, okay? So do we have equal group sizes? That's the question.
You're not gonna have exactly equal.
They're not exactly equal. What's our threshold?
Where are you
Above
seeing this?
1.5.
This is the first thing that got printed out.
About 0.05.
So remember, we're comparing the group, the largest group size to the smallest
Oh,
group
so
size,
divide
and we want it to be less than 1.5,
1.5.
right? So what's the biggest one? I'm seeing it. Boston has 22.05, I think Boston's the biggest. The smallest is, I see Texas with 1816, which is definitely smaller than 1.5. So we're okay on homogeneity of variance. Okay?
Where were you finding those numbers?
Yeah, mine
Oh, you know what? I ran this before you guys.
Oh,
So this was
okay.
separate from the Explorer.
Okay.
This was a frequencies.
Oh, that's right, yeah. I have it right, I have it.
I was just looking to see what Colorado was listed as to why it wasn't showing up. All right, let's go ahead and do the analysis of variance. So we go to Analyze, Compare Means, and One-Way Anova. Okay, we're doing hit distance by location.
They're down at the bottom.
Yeah, yours says stadium location.
Are we
So
doing,
because,
why do I have location?
just even though we have more than, just like our cards, just because there's more than one location, but it's just one variable.
Yep.
Okay, and it's still gonna do our columns and graphs and all that. Okay.
So once we've done that, the hit distance and the stadium location, we can hit okay, or do we do the?
Nope, we're gonna, yeah, let's look at the post hoc. Okay, we need to come back to the slides for something on the post hoc, because we didn't discuss this yet. So,
LSD.
the LSD is a good one. Huh? Okay. So, you see in SPSS that there are a ton of different post hoc tests. The challenge is trying to know which test is best to use in which situation. So this slide helps us to do that. Okay. Here I have a number of different tests listed in the middle, and in the left column it says the context in which to use those particular tests. Okay. So I'll say this first. If you have equal group sizes or roughly equal group sizes and similar group variances, then the most desirable post hoc test to use is Tukey's. Okay? There's actually, I think there's two.
Not REGBQ or whatever.
So the regular Tukey, not the Tukey B.
I think it's a second.
Guys,
So, Donnie,
Yeah.
are these the things they listed in the book, like most conservative to least
Yep.
conservative? Okay.
Yep. So the one that is the most conservative is the Bonferroni. Okay? So if you're making fewer, oh, that's pretty good, right? And that goes along with the Wahlberg here. You don't need that Bonferroni girl. There's no comparison. So if you're making fewer comparisons, or you have fewer groups, and they have roughly equal sample sizes, then Bonferroni is a good one to use. But we have a lot of comparisons that we're making here, right? We have a lot of groups. We don't have equal group variances, so we probably don't want to use the Tukey or the RGWQ. I would say we have slightly different sample sizes. The homogeneity of variance might be violated, even though we have equal group sizes. So I'm going to run Gabriel's and the Games Howell, both of those, and kind of compare the results.
So there's no Bonferroni for big groups. Bonferroni's only for small groups. So if we have
For
big
fewer number of groups.
But we're too big for Bonferroni.
We're comparing 30 different locations, so that's too many for Bonferroni.
So you're gonna do
What would be your number?
We don't have Games Foul. It's not even an option.
5?
Yeah, we do.
Yeah, you do. It's in the bottom.
Oh, okay.
Post hoc?
5 for a single Anova for single.
Yeah, I'd say probably 5.
Games Foul was on
Okay.
the bottom.
Bottom, of course.
Gabriel and Games Howell. Okay.
Oh, we're not picking Tukey?
We're not using Tukey
Okay.
because we had back here we don't think that the group variances are the same. So that's something we would need in order to run Tukey's test. Okay? And we saw that from the Levine's test, right? It was significant.
Okay, but didn't you say that we can just ignore the Levine's test and go down to the Wallace? Well,
We can use the Welch, but the Welch is for the overall, the omnibus ANOVA. It's
Okay.
not for the post hoc.
Okay.
I probably missed it. That's probably not what you explained. It's
So,
all been always.
I mean, do we even really know these well?
I would know that the slide is here so that you can look at your data and come back and say, okay, you know, I don't expect you to memorize all of these.
To know, yeah.
So, how does this, when we get to, how does this test validate that Colorado has a longer element, longer hit distance than the Wells? A skeptic might say, well, it's because they have better hitters. It'd be like taking all of the three-pointers ever made in the NBA, and, well, clearly, if you go to Oakland, you're gonna get more three-pointers, so that's where you should go, because that's where you make the most. Well, we all know that's not because they've got the best shooters in, right? They've got the splash
So, how would people respond to that? What do you guys think about that? What are you raising there? Those are other variables that you,
Yeah, there's
They're
other.
moderate.
those are confounding variables, right? Because if they're not accounted for, then they're going to bias the results, okay? With the analysis of variance, we're limited in how many variables we can include and what type of variables, right? We mentioned, right now we're doing a one-way, which means we have one independent variable, that's our location, and our dependent variable is the distance that they travel, right? We can do a two-way or a three-way to add a couple of other categorical independent variables, but what you're getting towards is the reason that we use regression analysis so much is because regression allows us to test these individual relationships, but then it allows us to control for the players that are on the team. So that's something that we had to do in my son's science project. The way that we did it was we compared hits that were hits at the same launch angle and the same speed. So it didn't matter who the batter was. The ball is saying we're comparing balls that are coming exactly the same off the bat and how they travel differently in these different
That's how you
conditions.
took out the confounding factors.
Mhm. So you basically include those things in your model. Once we get to regression, we'll be doing that, and then it holds all those other things constant and allows the only other thing to change being that one that you're interested in.
So you have the control.
But you're right, we don't have the ability to do that in ANOVA. In ANOVA, so sometimes t-tests and ANOVAs are used as kind of your first stage to say, let's say we don't know whether balls travel farther in Colorado or Oakland at all, and you know that's what we want to answer first. We want to know if the balls even travel farther, and then once we know that, then we can uncover more about why that happens and what's going
So
on with more advanced
Our
models.
dissertation data, we would start with these types of tests, and then advance to, you mentioned, Kristen, you were going to use a regression.
But we already
Yeah.
know I'm using a regression because of how many confounding variables.
But for that reason, because yeah. So I could give another example. Well, actually, I hope we have time to get to reading through some example dissertations today. But one is Trevor Wilson's, who just recently completed his. And so his question was, do different student athletes at BYU have different levels of trust, basically, was his kind of overarching question. And one of the things he was looking at was, are there differences across athletic teams? So are football players more or less likely to trust than softball players or women's or men's basketball players and so forth? And so he started with some t-tests and he moved on to some ANOVAs, but then eventually his main analysis was with regression, so he could hold a lot of the other things constant. He was accounting for things like student GPA, whether they're on scholarship, whether they're members of the church, and all of these other things. So oftentimes we're using these different tools kind of in combination with each other to tell us different things.
Do you define significance?
Yeah. So he found, so in the cross-team comparisons, he found the lowest, what he calls propensity to trust, or within the literature is called propensity to trust, on the men's football team and the women's softball team. Those two were far below all the others in their propensity to trust.
Trust whom? Trust what?
Trust in general.
So it's based on 4 questions. Anyway,
Did he control for like ethnicity and?
in the Anova, no, but then later on in the regression, yes. Yep. So he had
the
a.
Anova first just to see if there was a significance,
Yep.
and then it ran to regression.
Yeah. Yep.
So remind me, didn't he start, he didn't, correct me if I'm wrong, he didn't know he was gonna end up doing regression.
Correct.
Because he started with the Anova.
I told him he had to do a regression.
Okay, I remember that conversation with him, and then he
Yeah.
was like, and then I had to get this whole other,
Yeah.
and is that typical, where it's
Mhm.
like you get, and then you realize, okay, we better dive
Yeah.
Okay.
Yeah. Okay.
I think most
Just to show first.
question. Okay. Well, should I have, like, I mean, I think, like, should I do the Anova to show that there's going to be a difference and then go into the regression on my particular, or should I just?
So the
go
question
straight?
is which groups you would want to be comparing on which outcome variable.
And so I would maybe do
So
it.
potentially, yeah.
Okay.
Yeah. Okay, let's run this. You guys are finding how easy it is to distract me, and it's not good.
No, this is good though, it actually helps me conceptualize
Okay.
what we're doing.
Good, good.
Oh, sorry, guys.
Okay, let's run this. Okay, the post hocs are going to be crazy.
Now I want to just do this for fun.
So, it will give you a small table like this that says Anova to start. Do you see that?
Says it's significant, but is that because there's,
The sample size.
yeah, some,
It's possible, yeah. But also, it's possible that it's because there are so many groups, right? That it's easy to have a difference between at least 2 of those groups, right? So then, there's not much more to interpret from the Anova. It tells us we can reject the null hypothesis that all 30 outcomes aren't the same, right? The outcome of distance, so what we're measuring is how far the ball travels. It's not the same across all of the cities.
Where,
Right.
what tells us that on that Anova test?
The significance.
It's so small.
and actually none of them are significant.
None of the individual
There's
ones.
so many.
Uh-uh.
So there are some, but let's look through together, okay? So are you starting with, so this first thing that we're seeing, it gives you this stadium location. It is showing Arizona, okay? That's the comparison group right now. So basically it's comparing Arizona to every other city and saying, do balls travel farther in Arizona or less far in Arizona than all of the other cities, okay? So here you have Atlanta. So what are we looking for here?
Below 0.05.
Anything below 0.05?
Oh, that's-
There's also, SPSS gives us a little tip in this. We can look at the mean difference column. Look, once we get down here to San Diego, you see the mean difference is 11 and it has a little asterisk on the end. And that p-value is below 0.05. For any significant ones, it gives us an asterisk. Okay.
Could you like put it in Excel and just sort it?
Yeah, I guess you could.
Yeah, it's just those two.
I mean, most of the time, you're not going to have this many groups, so it's easier to kind of parse it out.
Colorado has an asterisk.
Okay, so let's compare Arizona to Colorado. Actually, there's no difference between Arizona and Colorado, right? And also, I'll point out, this is the Gabriel's test, okay?
It's interesting because I only did the 3, and there is a significance between Arizona and Colorado. Okay.
There shouldn't be.
0.045.
What does it say the mean difference between them is?
Negative 6.07.
So
Seven.
it's lower in Colorado? The mean is lower?
It's because we have a larger sample size, and so the significance goes.
So
Well,
it's
you know what,
saying, okay, this is what it's saying. It's saying the distance that the average ball travels in Arizona minus the distance that it travels in Colorado. So if it goes farther in Colorado, you're gonna have a negative value here. So that's what it's saying.
So
And it
Colorado's.
So it goes farther in
opposite.
Colorado than Arizona.
So then.
Although, no, but here it's saying it's not significant. Did you run Gabriel's test, Mike?
And Games House.
But the one you're interpreting now is
Gabriel's.
Gabriel's.
So then it's shorter.
It's just,
than the-
it's .045, but it's the inverse of that. It's the inverse of,
Here, let's look
.045 is
at-
the inverse of .994, right?
Oh, okay.
But Colorado, let's look at Colorado. So here you can see Colorado. Where'd it go? That it's different than a lot of stadiums, right? Because they've got asterisks on all these. You see a lot of significant ones. But
Which means the ball.
yeah, I have no idea why mine would be different from yours. Let me,
'Cause he just ran.
once you've done that, here, let me ask you this, Mike. Do the descriptives menu and run a frequencies on your location.
I don't want to sidetrack anybody on this either, maybe it's.
Well, my guess is that your sample's slightly different when you selected your cases. That maybe you've got a slightly different sample. Well,
It's all right.
actually no, because the mean difference is exactly the same. But anyway,
It's okay.
okay. So let's look at Colorado. Does everyone else's look the same as mine? Okay, so here we're comparing Colorado. Let's compare it to Atlanta, right? So the difference is 13.0, and the p-value is 0.035.
Is the 13.0, is that feet?
That is feet.
So,
So ball is saying that line drives and fly balls are traveling 13 feet farther in Colorado than they are in Atlanta. Okay? But back to Mike's point, this is not accounting for anything like who the players are. It's not accounting for how hard the balls were hit. And so there could be confounding things going on here. We're just looking at the distances right now by cities. Okay?
And that is significant.
It is significant, right?
because you think Philadelphia being the lowest would have the biggest difference in distance,
What's
Right.
L8?
and it doesn't.
But it doesn't
Angels.
when we're not accounting for anything else.
Because
Los Angeles.
Phillies had a lot of people that had power hitters were there.
It's also not considering time, right? Because this is across the whole season. So balls travel farther in the summer than they do in winter, right? Maybe there are more hard balls hit in Philadelphia in the summer or vice versa, right?
Double headers.
Yeah, so there's so many things that come into this that we're not accounting for right now. But is it clear how at least you interpret these post hoc findings? It's basically showing who your comparison group is in this left column to all the other groups and how significant they are. Then the confidence interval is telling us we think that here's the funny thing. We're in a situation here where we technically have a census of 2018, right? Because you try to think about what's our sample versus our population. We're looking at every single ball that's hit in Major League Baseball in 2018. So in some ways, we might not even need a confidence interval. We might just be able to see the data in the sample and say that's the reality, right? Unless, the thing that could change is across years, right? We're not accounting for any differences across years.
And then you get into
So there we have a
they've
different
had
population.
issues of baseball being wound tighter one year
Yep.
than the next, depending on where they make them. One year they were wound tighter in Puerto Rico than they were in wherever, and the baseballs travel farther.
Yeah. Yep.
Fine.
Okay, so
So it is.
that's the ANOVA and post hoc in SPSS. Questions there?
So the p-value, the third column,
Yep.
just help me understand what that's telling us, because I thought the p-value was static at minus, or less than 0.05. So the t statistic,
I'm not saying that right, I'm sorry. I'm just trying to figure out the third column versus,
Okay, so we're looking at still Colorado here.
yeah,
So let's compare Colorado and Atlanta again. Their mean difference is 13,
right,
right? The t statistic is 2.3,
right.
and the p-value is
Can you
0.035.
translate 2.3 into what does it mean? Like, we know the
Okay, so
13
that's
feet
the
farther.
exact p-value,
So-
but it's still under point zero.
2.3, that's just our observed t statistic.
Is that
Which is
standard?
Got it.
at the asterisk.
Not the standard deviation?
No.
Okay,
Right,
so
so when
that
we're,
is-
And you're right.
when we computed our f value here, right, that's just to compare our observed value to our critical value,
Got it.
right? That tells us how we know when it's significant, okay? This is the, oh, sorry. No, that is the standard error. That's not giving us
2.3
the,
is the standard error?
yeah, sorry.
Oh, okay.
That
And
is
it's
just
standard
listing the
deviation.
standard error of the mean difference.
Right. And we're saying the same thing if we say standard deviation.
So no, it's not the standard deviation. Remember, the standard error is the standard deviation of the sampling distribution. Okay?
I'm gonna pretend I never asked that question.
As opposed to the standard deviation is for the actual sample data. The other way to think about it, Mike, is the standard error is what we think the population standard deviation is, well, kind of.
It's the bigger.
Yeah.
So-
It's the whole population. We're
Yeah.
talking about the whole population.
Well, the sampling distribution of what that population mean is.
But the
Yeah.
confidence interval does tell us, because you can just
So
track
but the main thing is the significance here, okay? Think about, Janie, think about the significance like a p-value for a t-test.
Right,
Because essentially that's what we're doing. We're comparing, it's like doing a t-test between Colorado and that one other location.
so
So
anything that's under 0.05 is going to be significant.
it means that's a significant difference. We're saying the balls travel farther in Colorado than the other city when they're significant. However, if we compare it to the Los Angeles Angels, it's non-significant, so we say that the balls travel the same distance in Colorado and and Anaheim, which is where they
Did we
play.
say that, or we just reject the null? I mean, we would accept the null, but they're just equal.
Right.
We would
So
really say
here,
it's
the way you usually would report an ANOVA is you report, right, we have the two pieces. We have our omnibus test. This is just for the null hypothesis that all the group means are equal, right? So this was group 1 is equal to group 2 is equal to, right, this is how they write it, equal to group K. For however many groups you have, that they're all equal, right? That's this. In that first table, that's the significance here. That's our omnibus.
That's between groups.
That's between all of the groups. That's telling us that the balls don't travel the same distance in all 30 cities. Okay? I mean, so that's kind of like big whoop. I mean, would we expect the balls to go the same in every single city? No. We really want to know which cities are different, right?
But if that ANOVA test was 0.7, we'd say, well,
Then we know that they're all the same,
And we
balls travel
retain-
roughly the
and
same.
we retain
there's
the
not a
null
significant
hypothesis.
difference.
And then there's no need to do a post hoc because we know they're all equal.
So in getting back to Kristen's analogy, when her ANOVA came back 0.08, she would say, there's not a real difference between students.
Correct.
that take it."
So
Yep.
there's no need to then run a regression, because you're,
There is still need to run a regression because this is not accounting for any confounders.
so once the confounding variables are accounted for, then that could drill down to where you get a significant correlation.
Yep, and I will tell you that once we start controlling for things, there is a significant difference between Colorado and Arizona,
Right.
even though it's not showing up in my results.
So she could say something like, on the outset, it doesn't appear that there are differences between students when it comes to American Heritage. However, when we do a regression and extrapolate or take these variables out or control
Yep.
for them, we find that's good.
Exactly. Yep. And then when this is significant, now you want to say, okay, which groups are different from each other, right?
Helps.
So then we would want to say, I'm going to pretend that we don't have 30 comparison cities here and say, let's say we were just comparing Colorado,
Well, I think that's why I got a different.
Arizona, and Atlanta.
I think that's where I got different because between those three, there's some significance.
Yeah, I don't know. I'm going to mess around with that a little bit and see. But anyway, if we were just comparing Colorado, Arizona, and Atlanta, then we would say, you know, our results said that not all the means were equal, and we can see that the difference is between Colorado and Atlanta. Those two are significantly different.
So is an omnibus the null hypothesis for Anova tests?
Yes.
Okay,
Yep.
sorry. I did
No, you're good.
all-
No,
You
that's
got
good.
it. You got it.
It's, that's a good way to say
Say
it.
that
So
again.
I said that omnibus is like the null hypothesis for Anova tests.
Mhm.
And then the number 2 there is the post hoc.
Yes.
but we still say the analysts that there's no difference. They're equal. We're saying the same thing. It's just a different.
And do you have
Yeah.
to report which post hoc test you use?
Yes.
So it's the same.
And the post hoc would be written out.
So here's an example. Where? So here's an example of reporting ANOVA results. There are statistically significant, this was a different one we were using, regional differences in the amount of math taken by students. So you give the F statistic, well, you get to say that it's an F with the 2 degrees of freedom here. And then this is the F statistic, so this would be the 12 with the p-value, and then explain in context what it means. So for us, we would be saying that there are differences in the distance that balls travel by city. And you could give the p-value, well, the p-value is given for that. There is an effect size for the omnibus ANOVA test, of course, right? We've got our Mark Wahlberg here. It's just the sum of squares between divided by the sum of squares total. Okay? And it comes from that ANOVA table. So here,
Still less than 2, or the same?
so
percentage?
it's, I think it's the same benchmarks, yeah. So the sum of squares between, it's really big here, right? Because we have so many observations. But it's the sum of squares between divided by the sum of squares total. That's listed right there.
And where was it listed? What was it?
So in the ANOVA,
Yeah.
And that has to be greater than.
the between divided by the total,
And then where do you see that on that?
it doesn't provide, we have to calculate it. Yeah.
And what is the significance?
So
of
do
that
we want
effect
to,
size?
do you want to do that here?
An
Gonna
effect
do
size
it.
of 1, the closer you get to 1, that
The
means
less
it's a
effect?
huge effect, right?
Yep.
Less.
Closer to
Oh, the
0
number,
is
like,
less.
okay, the number
Yeah.
closer to 1, but
Yeah.
then it's,
Because if you have the total number of
Okay, I want to do this one real fast.
faces
Um,
of each other,
yes.
So between 829,
I'm thinking of half.
I think that's what I
190
yeah.
divided
And
by
they have some effect size that are greater than 1, but 0.4 is
330,
yours is
60.
different. You just see that's what you're expecting. But there are some way above.
Right.
Okay, so I calculated it on this. It's 0.002. It's
So
tiny.
not a large effect.
Nope. It's very small.
So there's a difference, but it's not really a big deal.
But the post hoc, so then we can also do effect sizes for the individual differences. The
Because
post
that
hoc
was
test.
between all of this.
Exactly.
But if we did individual, like Colorado and
Yep.
whatever, then it might have a bigger
So
effect.
the interpretation of the effect size is slightly different now, because it's saying, it's measuring all of the variation that's accounted for, so all the variation in the distance of the balls, that's accounted for the between group variation. This, in other words, it's saying, of all of the things that predict how far the baseball goes, how important is the location to that? And it's not very important when we're not accounting for those other things.
Right now, we're
No,
just
right now,
location.
it was 0.002. So location right now is explaining 0.2%, right? Yeah. 0.2% of all the variation in how far the baseball goes. So it's very little.
How did you get that number?
So that's
It's
from
just
this. You
Oh,
take the sum of squares between and divide it by the sum of squares total.
Oh, you,
So I got it from that
You-
chart here,
And you have to calculate.
and we have to
But
calculate
the
it.
sum of squares between are just the distances between stadiums, the 13, 11, and -8.
Yep.
Some
And
of
even
those.
if it'd been
Yep.
2, it still would have been small, right? 8's small, I mean, it's 0.2%.
2%,
but
even 2%
it's
is
still
not a
small.
ton, right?
And the baseball, the total in this baseball example is that 33, what is it, million?
It's,
3.3
yeah,
billion.
whatever it is, that's the total.
That means the balls in this sample size, in this sampling, were hit a total of 3.3 billion feet.
No, that's saying, so remember, that's this.
Taking those
That's how much total variation from the average. So that's saying, remember, it starts with the grand mean. So this would be looking at all 60,000 of those hits and saying, how far did they travel on average?
Okay.
Let's say that they went 200 feet on average, right? And then they take the total variation, right? So remember what we did? You take every observation. So you take observation 1. Let's look at it real quick. So where's our data? Observation 1, the hit distance was 339. So we do 339 minus 200 squared plus 60,000 of those, right? That's why
That's the
that number is so
3.3
big.
billion.
That's why that number is so big. That's the total variation in the data set from the grand mean. And now this is saying, of all that variation, how much is between and how much is within? You can see that way
Within's
more of
pretty
it's
close.
within than the between.
Alright.
Okay?
And that's the next one.
Yep.
yeah, the orange. Yellow or pink? Yellow.
So this is so this is called eta squared. This figure here.
ETA squared.
Yeah, it's a Greek symbol, eta, ETA. It's basically saying how much of the total variation and how far the balls travel is accounted for by what city they were hit in. And it's very little. But I'll tell you that a lot of this is because there are so many confounding variables that are canceling things out right now. The city does actually account for quite a bit more of this in reality once we start to
Once you
address.
take out all the white noise and the noise there, you just distill it down.
Yeah.
So did your son have to run a regression then to get rid of the confounding variables?
That's nice how you
I know, I did.
He did, yeah.
Such an adroit young man.
And
Very advanced.
you guys have got me so off track here that I might as well just
Good.
show you.
Just science fair project.
Actually,
My biggest fear is though that I'm gonna be blamed when we have this next test,
This data
that we
set.
didn't cover any of this in class.
It just means we
Yeah,
have.
So-
that's what I'm gonna write my test.
Is this
What
like-
will
Is this like
happen-
an Eagle Scout thing where you get a science fair pin ribbon too?
I wish, that'd be awesome. I want a trophy, man.
Did any other kids do a regression?
So, I think what it will mean is we push, well,
I just think this, I get this way more just because.
Good. Good.
I agree, that it's something you can.
sink your teeth into.
What's the factor in the defendant, or the defendant, we know which defendant. You know what I mean?
Yes, we know.
So is this your son's, are you gonna show us your son's project and what he found?
Yeah. Let me just pull up the results for you real fast.
Sorry, Donnie.
This should be
All right.
written and published.
I mean, it's Saturday afternoon. You guys are like pretty much
on
spent,
digital
right?
display or did you trifold?
Very-
Oh, it was a trifle.
Correlation between the number of
TV and
the
everything.
number of consecutive hours in class and the ability to pull the professor off of
Yeah, the sad thing is it's being all recorded too. It's out there for the world, right? So we'll just apologize to Catherine.
Sorry, Catherine.
She had her baby on Wednesday, everyone.
Congratulations.
8 years from now, you'll be doing their science fair.
Start thinking right now, right?
Let's see if I can even find this.
My fourth grade science project, whether plants have feelings.
My question is,
Plants have
Actually, no,
feelings?
I'll tell you, not today, but someday, it was, we got second place.
Did you run a regression on it?
No, I didn't know all this, but we did put the plants under polygraphs, we used polygraphs.
who in their right mind?
Okay.
Oh my god.
Okay, so there's the title of his.
Is this being paid?
Tate is his
This is
name.
probably better than most papers I've seen submitted by
It's a
college.
bummer that Tate does a home run. Tater, you ever call him?
Yeah,
Tater?
exactly. Yep.
It's a home run.
Oh, is that a home run later?
Yeah, home runs a tater. Okay, so there are his hypotheses.
Oh my gosh.
We did this background research together to find out, how elevation would affect it. So we found this stuff before. So as you move to higher altitudes, air pressure decreases significantly, about 3% for every 1,000 feet of elevation. Not really, I guess, yeah. So baseballs should travel farther in warmer temperatures and in higher humidities. Okay, guys, get ready for this.
I love that you actually put the team colors as the actual thing.
Oh
too.
my god.
Well done, sir.
Not only, we weren't just eyeballing these two guys. Let me
Did
show
you get the
here.
actual RGB color? Oh,
So my kid's room.
What does that mean? What translates?
Okay, I'll show you
It's
here.
the authentic MLB
Yeah,
color
so
wheel.
each color has its own name.
They're
So
patented,
can you just go and get a
trademarked
purple
colors.
So
color
if you
on the
want,
wheel?
if you want something to be in Dodger blue,
Actual.
It's
I
hex
didn't
or
know they even
RGB
had
or.
such a
Okay.
thing.
here you can go Los Angeles Dodgers. Their RGB is 0, 90, 156. Okay, so then when you're in Word, you can go
You do this in Photoshop.
to your color here, right?
Oh, and go put it in the thing.
And then when you're in your colors, if you go to more
I had no
more
clue.
colors, you can put in the RGB
That's
values.
super
Wow.
That's maybe the wow.
So for people, I'm really into like visual design and stuff, and this is really big in that.
The
So
Pantone and everything.
Well, it's good that
I
somebody
didn't know that
knows
existed. I didn't know that.
I'm glad I could validate.
Yeah.
I know.
okay, so there's the differences in elevations across stadiums, and you can
That's
see.
not the colors on my calendar.
So there's the advantage that Colorado has. Here's
What do you
the.
use? You mean UVU colors has their own.
Oh, yeah, there you go.
So is BYU.
Yeah,
Yeah.
BYU has its own.
Yep.
Liz, did you know this? I mean, you knew the BYU had a blue, but did you
Oh,
know that
yeah.
it was like,
RBG.
It's like you create your own.
You have to know that.
Oh,
Because you have to
the
use it, and then
ABP
you
came
have
down
to
on
use it.
us and like did
Because you
a
can't-
logo police.
Oh yeah, it's
Rated our whole
serious.
thing.
It's serious
You know, sliced
business.
us up.
were you using
What
the
is yours?
RGB colors?
stop.
Oh, it was bad. We got our whole logo tanked. We had to spend like thousands of dollars every year.
Hey.
So font.
Oh my
They sell it.
goodness.
Stratum one.
Linden actually sells the RGB.
Wow.
Blue, orange.
All right, so here is.
Oh my gosh.
So- The average home run launch speed
Tate,
in
man.
2018 was 103.5 miles per hour.
Tate will be teaching at BYU
The-
here in the next 2 to 3 years.
The average launch angle was 28.2 degrees. Okay, so we held all this constant basically.
Was that only for Bryce or was that all of them?
That's everyone in MLB, every home run that was hit. And so these were the results. So holding everything constant, you're comparing just balls that were hit at the same speed and launch angle across locations, holding constant elevation, temperature, and humidity. If everything is equal and the only thing that changes is the elevation, for every 1,000 foot increase, the ball goes 4.4 feet farther. So Colorado's like 5,000 feet far higher than most everywhere else, so the ball's going to go about 20 feet farther, all other things being equal.
Do you know if, when they're building stadiums, do sometimes they take that into consideration in terms of how far? or
So
close
Colorado
they are?
adjusted their fences about 5 years ago or so to try to account for the fact that way more baseballs were being, or home runs were being hit there.
Yankee Stadium tried to do.
Yeah,
So they're gonna
they
do the same
definitely
thing,
do
right?
that.
Something like that.
They got the short porch and right, I mean, Yankee, yeah, it's a big,
Yeah.
big deal. And
Yeah.
that's another reason why no pitcher wants to go there if the fences are short because their ERA is low.
Right.
So temperature
They lose out on
matters
$3 to $4
too.
million a year for that.
So if you increase the temperature by 10 degrees, the ball goes 3.1 feet farther. But the difference is not as big in temperature across places as, you know, where Colorado has the huge advantage there. But you'll see more home runs in the summer than you do in, you know, April and May and October.
Dew point makes a difference.
And the dew point, yeah, the dew point also makes a difference, but it's much smaller.
You want a hot, humid day in
A hot humidity
In
in
Denver.
Denver.
Yeah,
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 they don't have
that's
humidity,
ideal.
so they're not-
thunderstorms
Yeah,
and
maybe that.
it's monsoon stuff.
Yeah.
But even if it's cold, then the dew point's not gonna matter.
Couple of
So
rainy
even
days
coldness
in a
doesn't
row.
matter.
True. Some heat coming off.
Which you would think it would.
Okay, last thing on Anova, you can do effect sizes for the individual. Remember what we called these when we compared just two of the groups?
The Cohen
It's a pairwise comparison. And for these pairwise comparisons, you can calculate Cohen's d to get the effect size. So if we want to know, you know, we saw that the difference between Denver and Atlanta was like 11 feet. Is that a big difference or not? We can use the regular effect size calculator online to do these, just using the means and standard deviations.
Which do we use if it's not to a pair?
Sorry?
Which we use if it's not a pair? What do we use besides Cohen's d?
There was something
For
about
for this one?
Division
For the
thing.
non-
For the overall test, the omnibus test?
No.
For the
Yesterday,
effect size, yeah, there was something else you talked about.
there was a non-parametric, you couldn't use Cohen's d. You couldn't use the online calculator for Cohen's d. You had to use.
So that was for the dependent t-test.
Dependent t-test.
Yeah. So here, we can use the online calculator, the Cohen's d, for the post hoc test to compare individual groups.
Okay, so you could have a whole bunch of different teams and just rank the two individual, you could just go and skate for it.
Yeah.
Okay.
But then for all the significant ones, you know, would want to say that the Colorado, the balls go farther than Atlanta and this, and for all three of those, we would want to list the separate Cohen's d.
So separate points each pairwise.
And what's Becker's? What is that?
Oh, Becker, that's just the person that made this online calculator.
Oh, okay.
Yeah, that's, sorry.
Every little thing is like, what is this now?
Someone's thing is, yeah. Okay,
We take
let's take a 5-minute break.
whatever's been there.
The question is, what are you going to do this year for science fair?
Well, we just finished that like 2 weeks ago,
Oh,
and
okay, so you
now,
have a year.
so it's a year from now, but still, that's a big question, I don't know.
Shouldn't have started so strong out the gate. Because when you're doing, like, which cookie do you like best?
I know.
It's a bit of a letdown.
So Donnie, remind me, I know my sister, somehow my sister and you guys are connected. I don't know if you're in the same
I think
state.
it's your sister and my sister.
Oh, maybe
is the
that's what it
thing.
is.
Yeah,
So Emily and Logan Deans. Yeah, and your sister's
Jess
daughter-
Rogers.
Jess Rogers, and maybe, I think they have a kid the same age or something.
Okay.
Does that sound?
Yeah,
awesome?
I didn't remember it, how exactly, but yeah, it was through my sister.
Where does your sister Jess live? Is she in Provo?
Yep. Yeah, they're just down, you know where Will's Pit Stop is?
Yeah.
They're just right
Oh,
by
yeah,
the steak
okay.
center there.
Okay, then they're probably in the same ward.
Yeah,
Is that, okay.
yeah, I think so.
Okay, cool.
Yeah, so does your sister live in that neighborhood right off the roundabout?
Yep. Yeah,
It's a nice place.
it is. Yeah, yeah, it's nice. Yeah,
Do you live in Provo?
Oh, no. I mean, I did my time. No, I live in Pleasant Grove. I have a condo out there. I've
Okay.
lived in Pleasant Grove for like 10 years now.
Uh-huh.
So,
Nice.
Provo's great, but, you know, late on a Saturday night when I'm doing my grocery shopping in my sweats, it's nice not to run into.
Yeah, for sure.
That's pretty sweet with those colors. We paint
It's
our,
pretty
we're
fun.
New York Mets fans, in
Uh-huh.
our house, and my boys are fanatics. They would love this. But they want to paint their room, so we got the actual Glidden paint colors. Glidden has all the MLB colors in
Uh-huh.
colorway one.
That's
So
cool.
we did their room with Mets colors.
Yeah, that's super fun.
Mike, let me know, well, either of you, let me know, like, if you guys ever wanna go to BYU baseball games. 2 years ago, we were really good, last year was a little bit of a struggle.
Yeah, last
But
year was disappointing.
It was totally disappointing. It was
Do they charge for volleyball games here?
Uh-huh, but same thing, just text me.
Oh, really?
For football and men's basketball, it's a little bit trickier, I
Mhm.
need,
Of
you know,
course,
like,
of course.
but for any of the other sports, if you wanna bring your family, just text me, give me a little
Okay.
bit of notice, and I'll put you on the list. Yeah.
Awesome.
Yeah, because my son just made the volleyball team.
Oh,
at
awesome.
Harriman, so
Good.
he wants to come watch some of the
They're
BYU
so,
games.
have
That's
you been to
awesome.
the main gate? They are
Never.
so
I watch them
fun.
on TV,
Yeah.
and I get sucked in watching on TV. They're amazing. They're like
Oh.
just gazelles jumping.
Oh
up.
my gosh.
It's crazy.
They
so.
get so high, it's just.
Yeah, in fact, I was gonna
really fun.
see when the next game was. That's awesome. If you could do that. that
Oh,
would be
absolutely,
sweet.
yeah, no problem.
You'd love that.
Yeah, the baseball games, those are my favorite event to go to
Uh-huh.
at BYU. 'Cause
Yeah.
the kids, it's awesome. They don't even watch the game. They're
No.
all
They
like
just-
running around the
Yeah.
whole stadium. It's so fun. It's really
But
great.
you can,
Right.
it's low key, it's a great way to
Oh,
visit.
yeah.
Yeah.
Baseball games make a great, like,
A
date or
date,
family
totally.
outing.
For
because,
sure.
you
It's
know,
so, yeah, cause you don't have to be, it's not loud, you don't have to be right there.
Right.
It's beautiful, especially when the weather's nice and it's
Yeah.
sunflower seeds and Diet Coke and I love those, I love.
So great.
And the scenery, I mean, that backdrop in Miller Field,
It's
Yeah.
gotta be,
unbelievable.
it's gotta be the best.
Oh, it's
Where,
beautiful.
where's that?
Just our baseball stadium, just the football
Oh, here,
mountains in
oh,
the
yeah,
background.
oh, yeah.
Liz, do you know Brent Norton that does the
Not well, but
commentary
yeah.
for the BYU?
Yeah.
Yeah, I played ball with his son growing up. We were
Oh, you did?
on teams together, yeah.
Wait, 'cause
Where'd
went to
you
Timpview,
grow up?
right? Yeah.
Timpview?
Yeah, typically.
And I know we already had this conversation, what year did you graduate from Timpview?
02.
Okay, yeah.
And you said you were there
So I was there
after
and I
you
feel like-
graduated, right?
Yep, so I was working, so I was an assistant girls basketball coach there, starting 2000 until like 2004,
Mhm.
my master's year. But 1 year, my gap year in between undergrad and my master's, I was hired as like a hall monitor,
Uh-huh.
but I ended up turning it into like an academic tracker position and
Yeah.
making them back pay me for, because I made it into more, like I started tracking and then working with the kids that weren't going to
Instead of
class.
just yelling at them.
Instead of just, yeah, going in the hallways and going to go to class, like, this is stupid. So
Yeah,
I
that's
actually
better.
kind of mentored on the block.
Yeah, that's much better.
But then I looked online at the outside school, or the pro school, and I'm like, this is a job, like what I ended up
They
doing.
created it.
I'm like, no, like, this is a real job, you hired me to be this, but like, I'm doing this. And so I
Right.
made this case and they backed
They
me.
did it.
They
That's
did it.
awesome.
Yeah.
So
yeah.
which girls from those basketball teams
So
do you remember?
Lindsay Henson,
Uh-huh,
Amanda Valgartson,
okay,
Megan Callahan,
Uh-huh.
or sorry, it was Megan Valgartson, Megan Callahan.
yep,
Melissa Caldwell, Miriam Polkey, all the older ones, Megan Gorley.
okay. Yeah, most of those were like a year or two older than me.
Okay.
So
so
Megan
let me
Callahan
see.
was my age.
Was she? Let me
Did
see.
you have Alicia Murray?
Oh, I
on
love
the
Alicia
team?
Murray,
Yeah, we were good friends
Yeah.
growing up. Yeah.
Who,
Trying to
the
remember who
Reds,
else.
Sarah.
Oh yeah,
Sarah Red.
yeah, they were in my ward.
Were they?
Uh-huh.
Lindsay Freeze,
No, I don't think I knew her.
she might have been a little bit.
Oh, that's awesome.
Anna Perez,
Okay.
yeah, those are some fun years.
Anybody want a Honeycrisp apple slice?
I'll take one of those.
I'll take, I'm just, me too.
Save me one.
Sorry. Honeycrisp are my favorite.
I know, aren't they
They
good?
are good.
They were also
I like jazz.
created by my alma mater.
Oh,
The
really?
University of Minnesota invented Honeycrisp apples.
Oh, wow.
They did some
That's
cross
pretty cool.
pollination, whatever.
Yep.
So did you have, when you were there for English, did you ever have Allison Connie?
Mm-mm.
So she and her husband and me and one of the other assistant coaches always chaperoned the dances. And she was so great, and now she's like a famous Latter-day Saint author. I think some of the other teachers that were there. Chad, who was the football coach? Chad, no, he was the AD.
Van Orman?
Mm-hmm.
Yeah, he was still the coach when I was there.
Was he still, okay?
Wong took
Yeah.
over
Yeah, we
shortly
were-
after
Yeah,
that.
that's right. And basketball,
Wildebohr.
Wildebohr. And then Nate,
Mascot.
Nate
for
Warner?
University of
yeah, so
Minnesota.
Nate was a school counselor
Wildebohr.
there. Yeah, and I coached
My
his
dad
daughter
taught
at
there for
Notice
6
he was
years.
there.
Anthony, do you want a piece of apple?
Brad Monks,
Mhm.
was principal.
Yep, he's in my ward now.
Is he?
Mm-hmm.
Will you tell him hi? I don't know if he'll even remember me.
Sure.
But he was a really good mentor to me. Like, he was great.
What was his name?
Brad Monks.
I loved him.
He's a good guy.
He's a good guy. He was the assistant principal when I
Is he
taught
still,
there.
is he retired? Is he still working?
No, he's
I don't,
retired.
yeah, I think he is
I
retired.
think he's retired. I had two really rotten administrators at Two and I had Brad. He was
He
decent.
was just, yeah.
Yeah.
He was one of the ones that encouraged me to get my master's.
Hmm.
I did not love being at Symphony High, sorry. I know you're an alma mater, but I did it, because instead of doing student teaching, they were like, oh, Symphony needs a sub for the rest of the year. Instead of student teaching, we're gonna have you go do that. So I never student taught. I
Oh,
student taught
really?
for a
We
week.
just got thrown in.
And then they threw me up at Timpview for the rest of the year. It was tough. It was fun. Ron Coombs is on, we did it, but yeah, Brad saved my
Uh-huh.
life. He was good.
Huh.
I had two kids in my class. I walked in the first day and one had just had a baby, his girlfriend, and then the other two were married. And I'm like, holy cow, I'm like, one of them was only like 2.5 years younger than I was. But we had different life experiences, you know, it's getting to be where you.
Mhm.
Yeah. Who was the, Randy Merrill?
Randy Merrill was the principal and then he was the superintendent later.
That's right.
Randy
So-
was my
and then-
professor for one of my master's
Oh,
classes.
Was he?
Yeah,
And
he
then Jim
was a-
Campbell was the other administrator.
I think he was principal later.
He was- I
because
think he was.
Bayless was the principal while I was
Yes.
there, and Merrill was one of the assistants.
And Dr. Bayless, and he
Yeah.
insisted people call him Dr.
Yeah.
Bayless.
And
Yep.
Dr. Bayless also spent more time up at UHSA, I think, than he did. It seemed like
Oh,
when I
really?
started out, he was there all the time.
So the girls' basketball coach was Ray Scott. I don't know if you ever had him for history. He was
Uh-uh.
a terrible teacher. He's the kind of guy that gives coach teachers the reputation, because it was like.
Really?
Oh, yeah, it was all.
No, my
about-
history teachers at Timpview were fantastic. One of them, Stevenson, is still there. What's his first name?
Gary?
Yeah,
Yeah.
yeah, he's really great. My nieces still take his classes and love
Oh,
it.
cool.
Yeah, he does like AP geography and a bunch of other stuff.
Yeah, that was fun. Those were some fun years.
Suzanne may be, she was just answering a phone call out there, so she may
Okay.
be talking to like somebody, I don't know.
Well, let's get going. We're gonna we're gonna have to push our crosstab or our chi-square test for today. So we're gonna cover that a different day. We've got enough time to quickly go over the Kruskal-Wallis test, which is the non-parametric equivalent of Anova, okay? And actually, we're gonna do this pretty quick. I don't think we even need to go really into the detail of how to do it. It's very similar to the Mann-Whitney U test that we did yesterday, but now we're just doing it for multiple groups and comparing across those multiple groups. So here are the basics. So Kruskal-Wallis, it's based on ranked data, just like the Mann-Whitney U test was. We use it when we can't use Anova for either having non-normal data or having not a continuous outcome variable, right? If we have an ordinal level measure, we can use the Kruskal-Wallis test instead to compare differences across the groups. So like we went through yesterday, you combine scores from groups and then rank them in their order. And then you sum the ranks and compute the test statistic using that and the degrees of freedom. So the degrees of freedom in this instance are k, so the number of groups minus 1, as opposed to yesterday we were using sample sizes to calculate our critical value, right? So here's the example from the book. A researcher has sampled 15 students to score the effectiveness of 3 different video clips about safe driving. Okay, so the 15 students, so 5 students watch the first clip, clip A, 5 students watch clip B, and 5 students watch clip C. Okay, and they score the effectiveness of the clip from 1 to 100. Okay, so in this instance, it's actually a numeric outcome variable. So they must be using this because of some sort of violation of the assumptions, right? And my guess is since it's a small sample size, likely it's probably that normality assumption that got violated, which would be the reason they're using it. So I think we don't need to go through the details. You know, it's really similar to that Mann-Whitney U, where you group them, you rank them, with the highest score getting the lowest rank, and then you sum the 2 groups. And this is what, Kristen, you raised yesterday, where you showed in the book this table where they have the sum of the ranks. So here they've got the ranks listed for clip A, so rank 3, 7, 11, 14, and 15, sum to 50. The ranks for clip B, sum to 18. And then here, instead of the ranks for clip C, they accidentally listed the rating, right? So this should be the ranks listed here. The sum is correct, so they sum to 52.
But
the actual scores there should be the ranks from this column.
So clip B is good, but
Clip A and B are correct, but clip C
Clip C, if you
should
take off
be.
it should be 8, 9, 10, 12, and 13.
Oh,
I think
yeah.
that's what they did, they just added the 1, 2, 3, 4, 5. Yeah.
Yeah, you're right, because it's not the score.
No, it isn't.
Yeah, it's just a
Ranks.
typo. That's interesting.
Yeah.
Kristen caught
Okay.
that.
Huh.
Well, it took me 20 minutes to figure out why I couldn't figure this out.
This
I was like, I'm just gonna have Donnie.
So,
This is really interesting.
just looking
Yeah, exactly. I
at,
was like, how's this happen?
so if we just compare the sums for those 3 ranks, what would you guess would be the result of this test?
I'm not down for enough.
Clip A was more violent.
B
I mean,
would
clip
have
A
more
and
of
clip
a-
C are about the same, right? Their sums, so this one's 50 and this one's 52.
But clip B is gonna have.
This one is a lot lower in the sum ranks, which means their scores were a lot higher, right? So I would expect to see a significant difference on this test to suggest that there aren't all equal means.
But what what does a rating or ranking mean?
So it's saying how effective the clip was that they viewed. So that would be,
The higher the rate.
what the research question is asking is what's the most effective clip to show students, right? Are these equally effective, or is one better than the others? And from what we're seeing right now, it seems like clip B might be more effective, at least as reported by
This
students.
is like a golf score. This is where,
Oh, you want it low.
yeah, you want it low.
That's right.
Yeah,
It's just.
But, well, the rating
rank-
is high, but the ranking is low.
the
Correct.
ranking is
The
low
ranking is low
because.
Yeah,
because
it's
they're
like
top.
a seed,
It's-
you're a higher seed even though you have a number 1 versus 16.
yeah, exactly. Okay, so we get our test statistic by using this formula here. Okay, we don't need to run through it. I just want to point out a couple of things. There are a couple of constants in this formula. So up till now, anytime we've worked through, the F test, the T test, and we've computed manually our T and our F statistics, all the data has been pulled from the sample, right? Here you see 12 in this numerator. That's not dependent on anything in the data. That's constant. So anytime you run this formula, you're going to take 12 over the total sample size times the sample size plus 1. And then here you have this constant of 3. It's just how it works. So,
So that 3 is not
Anyway.
coming from anything?
no,
It's a constant.
It's just a thing.
yeah. So, anyway, you would calculate this, so you plug in the numbers, you use the total sample size, the group sample size, the total rank, so that was what's listed here, and the number of groups, right? And then you use a table here with the degrees of freedom to calculate that. But I don't want to focus too much on this. Let's just look at SPSS for how we would conduct it.
SPSS does do it.
Yes. Okay. So let's go to what data set are we using here? Let's open up the NELS data. Let's see what we can use in there.
Is it a problem that if you have the same data set in SPSS before, that you just go back to the data set source and bring it in again? Or should you use something that you would already?
Wait, what do you mean? Sorry.
So if we've used NELS before, and we
Uh-huh.
have some manipulation in SPSS, we've done that. Is it better to go back to that data file that you've already worked with, or go back to the original data set?
So that's a good question. And this is one of the reasons why people that do a lot with statistics and advanced stuff in statistics often don't use SPSS, because the way that it's set up in the point and click, the menu-based structure, is that it's really easy to change things and then not remember what those changes were, and then to not be able to reproduce what was there before. When you have sort of a code-based program, you can have your raw data set and then run things on the data set. It doesn't change the data set, it's just doing everything separate. So I would say, as long as you remember what, if you've changed anything in the past on the data set, then you just don't want to change anything and then later go back and be doing an analysis on a variable that you changed.
But it's not going to hurt anything to go back to the original data source and
Correct.
pull the data set into SPSS.
Correct. Okay. So let's say we want to test, let's find a variable that would work for us here. We're going to find an ordinal variable.
Yeah.
What are we doing now?
The NELS, yeah.
I had a really good friend named Nels growing up.
Oh, really?
Yeah, he went to Rice and now he's a filmmaker.
Good scan.
He's a filmmaker. He's one of his films in Sundance films. Nels Binger. He's like the grandson of, who was the governor? Norm Binger?
Yeah.
Or the great grandson.
More bigger?
I think so. Anyway, Nelson.
Okay, so, oh, why is my thing not showing up here? So now I got switched. Okay, so we're going to use as our outcome this late 12 actually, no, let's use the cuts. So cuts 12 is the number of times that a student skipped or cut classes in the 12th grade. So if we look, it's listed as an ordinal variable. If we click on our values, remember our little Easter egg in that values thing? We can see here, this is not a regular numeric value or variable. There's these categories, right? You have 1 to 2, 3 to 6, 7 to 9, 10 to 15, and over 15. And those groupings are not all equal. They're not all equidistant. And so
If they were, then it would have been a
Ordinal.
interval.
Could have been
Interval.
Yeah.
If it was once or twice, 3 times, 4 times.
Ideally, if you're collecting this information, you just ask how many times, a student missed, and you just have it as a continuous variable, right?
Right, instead of putting them into categories.
Yeah.
He was just showing.
But that's why they have it here. So what groups are we interested in? We could compare. Here's one that's got urban, suburban, or rural. Okay, so our question would be, do students miss more classes if they live in urban, suburban, or rural places? You'd say urban? Was that that's your guess going in?
Rural, you can tell, they're
Yeah.
smaller, so you know when people are.
Okay, yeah, I can see that. All right, well, let's test for it. So we go to analyze
True, that's.
non-parametric tests
I'm gonna say suburban.
and independent samples.
Wait, analyze.
Non-parametric and independent samples.
Skip the first page, that's the only thing I remember.
Skip the first page.
All right, hang on.
Skip the first page.
Oh, skip? And
Yeah, skip the objectives, move to the fields tab, up at the top.
Was it one sample, independent sample? Sorry.
Independent sample.
Thank you.
Okay, so our test field is going to be cuts 12.
So, go to our test field.
Independent samples normal?
That's from descriptive.
No, analyze non-parametric,
and then.
and then independent samples.
And then what do we decide for the group?
So then the group will be urban.
There it is.
Thank you very much. That was
Urbanicity?
Yes, urbanicity.
Yeah, urbanicity.
Yeah.
Cuts 12, where's cuts?
The label is number of times skipped or cut classes.
So remember, you can display the field label.
Yeah.
That little box in the top corner. You can toggle.
Okay.
Okay, so fields, I'm
Fields
not
is cuts.
seeing the groups
Cuts
that.
class.
Oh, number of times skipped. Okay.
Yeah, fields is number of times
You
skipped.
can
I'm
toggle
trying to
between
find it.
what's called.
Urban times late.
Number of times skipped or cut.
Yep.
Got it.
It's around 14 or 15 in the list.
That's easier.
I don't see
You
the
can sort it by alphabet.
There.
option.
Oh, did you do the independent?
Are they
No,
weighted?
independent
Oh,
samples.
Independent sample.
Why are mine labeled different than yours?
Yeah, so you.
Okay, Jody, right here, you can toggle whether you want to see the variable names or
Oh,
labels.
there you go.
Yeah.
Okay, just use that.
Okay, so once you've got that, go to the settings tab. Right, we don't want to let it boss us around and tell us what test to do. We want to boss it around.
Can we try?
So you can and see what it does.
Anyway, go on, I'm sorry.
So here's the thing. It will likely choose the correct test if your data are correctly listed here in the measures, but sometimes they're not, and that could be a situation where it runs the wrong test, and you might not realize. Okay. Okay, so we're doing Kruskal-Wallis, one-way Anova, right? And leave it in the standard that's there, the all pairwise, and run that.
Reject the null.
And then you.
Okay, so here's one of the nice things is it tells us what it thinks our null hypothesis is, right? So we're testing the distribution of the number of times skipped across categories of urbanicity, and that is what we're testing, right? Although it doesn't exactly say what the hypothesis is with that. The hypothesis is that they're all the same, right? That regardless of urbanicity.
So there is a difference.
So it's telling us there is a difference in the three groups, okay?
Tell us where the difference is.
Let's, so for Jody who wasn't with us, we've got some Easter eggs in here. You can double click on this table now and it will open up some additional stuff for us.
That rural.
That's cool.
The rural kids are good.
Whoa, wow.
Suburban.
What the heck?
It's too hard to skip in the rural district.
That's what I'm saying.
Okay,
You're
although
walking a long way to the gas
Right,
station.
and it's, where are you gonna go?
that's interesting. Where are you
What are you
gonna
gonna skip
go?
Well, and everybody knows everybody who's gonna call everybody.
That's
When
right.
it's a
I wanna
small
see that
school,
real
you
quick.
know who's missing. Never times skip.
So the mean rank between the two, if you hover over urban versus suburban,
Yeah.
does that mean that urban skips a little more times than? Because it looks like suburban's a little taller.
Looks like
Yeah.
suburban and urban though look pretty much like.
They're like
They're
5 points
equal.
different.
Right, and that's what we were, wait, never mind, sorry. We weren't using that same example, but it's kind of like what we saw in our example here, where the two groups were about even and the one group was
what's the
different,
outline.
right?
It's different.
Okay,
But what does it mean if you hover over it when it says the mean?
the mean rank,
I mean, doesn't that mean that urban is higher?
269. It is, but it's barely, right? I mean, they're really close to each other. There's a much bigger difference
I just wondered
for
if Cammy
rural.
had one. Cammy said urban, I said suburban. I just wanted to know who
Okay,
was right.
so how do we find that out? Okay, in an Anova, what do we do? In an Anova, what do we do for that?
We do the whatever.
You do it,
The post hoc.
Post hoc tests.
Yeah. and you
Okay.
can compare close to two
So we can do that here. It doesn't show up by itself, but down here, if you go to view, pairwise comparisons. You see that?
Yeah.
What does that mean?
Oh, so that's the
Nice.
third one down.
Look
So-
at
The post hoc and then the
urban
pairwise, right?
and
Yeah.
urban and rural and suburban and urban. It's gonna compare all three possible combinations.
Rural is,
So it's telling us that rural is lower than both suburban and urban.
Significant.
And it's telling us that there is no difference between
Suburban and urban.
urban and suburban, so you guys tie.
we tied, we both got it. Good man.
You two were right, yeah. Only in
Are these on
statistics.
your
you
slides,
both
like
can be right.
steps?
I don't know that all of these steps are.
I have a friend.
It's recorded, you can watch the.
That's
video.
true.
You're right.
Yeah.
Double speed.
How do you know where the, I know, Chris.
So I do have this, how to get to. So Kristen, this is what's on here. So it does say how to get to the non-parametric independent samples menu, that you input, your outcome and then your group, and then you select the Kruskal-Wallis. It shows the results,
It just doesn't tell you the pairwise.
but it just doesn't say, yeah, it doesn't show the pairwise, so.
Is the Wilcoxon in the same spot? No, or?
Yep, it
in
is.
that? Okay.
Yeah,
When you
so,
brought up that, third tab, you could select.
You could select it.
Constant.
yeah, here, let me show you.
Everyone just go ahead and pause for just a minute so I can.
So,
We're pausing.
Hey, this is nice.
This is where reminder.
Yeah, you've been leading the way on stuff. That's nice.
it will, here's the thing, it's not showing up now.
Because you have to.
Because-
choose.
That's not an independent samples comparison. So for that, you go to non-parametric related samples. and then
That's where that.
the menu is slightly different. So here is the Wilcoxon.
So it's under related.
Yeah.
Okay, that's why that.
So I did the automatic and it said unable to compute.
Really?
Yeah. And
Interesting.
then it picked the right test.
But it wouldn't run?
But it wouldn't run.
Huh. Wow.
On my
Oh,
palm.
I need
So,
to,
Okay.
That's
like,
cool.
I have this, and then, I don't know if it's in this one. It's just
No, I just need to have it like Tom Brady has his plays on
Yeah, that's
Which
perfect.
test?
Yeah.
Which
I just thought you-
do what he did, put him in background. This is the test. There's how we're doing it.
Okay.
How do we know if it's significant? I mean, if we just look at, oh, it's just the regular .00 would be,
Yeah.
two of them are very significant, one's
Yep.
not.
One's not.
Yep.
There's a huge difference between rural and suburban.
And urban. But who won? You or County?
We're
It's
tied.
surprising
It's a tie. There's no
It's
difference
significant.
between the two.
Significance is one. There's no
Yeah.
significance.
But it surprises me that,
Keep the
there-
null hypothesis.
there's a slight,
Those two.
a
On
slightly,
just those.
Conscious list.
this means that there's slightly more, cutting class for urban students.
Technically, Cammy is right, because there's 4 more kids.
You can't really interpret it that way.
Oh.
The only thing we can interpret is that there is a difference between those two groups, and that there's no difference between urban and suburban, because any difference we see is likely due to the sampling error. It just happens to be that we sampled kids, that are slightly different.
Okay, so you really couldn't, you can't really make correlations between rural urban and rural suburban with scores that close.
Correct. Okay, everyone feel okay with that? All right. So we have about 35 minutes. We're gonna finish with a little activity.
You said you wanted to talk about surveys?
Yeah, thank you. Okay. So you guys developed your surveys last semester, right? We want to use them in something we'll be doing in the end of March or the start of April. So if you want to use the data from your surveys for that assignment, I would recommend that you try to collect some data with those surveys starting now, okay? So I think the target we're aiming at, ideal would be a sample size of 100. If you could get 100 people to respond, that would be good.
You can't get 100.
Does it have to be random?
No, it doesn't have to be random
Oh,
for
okay,
this.
okay.
No.
You can't
All
get
right.
100.
Get them however you can.
Now, what about IRBs? We don't have to worry about it?
You don't have to do IRB. IRB is only required if you are publishing your research.
Okay.
We're not in
Yeah.
a bubble.
You
I'm
probably get
serious.
So do we want to just use one of ours, or do we want to use?
It's up to you guys.
We can do
Um,
schools, 8.
Hold on.
So Memo asked an important question, is whether you guys want to keep your 3 separate, right? Or just use one. It's up to you. But,
Oh, we wanna do ours.
okay,
I don't want to do one.
I don't know.
Yeah, I'll do yours.
Yours is good.
I want to get 100 and I want to be done.
well, here's the thing. This is not an assignment for class, so you're not required to do this. We have other data we can use for this same exercise if you don't.
Okay.
But it's,
I'm good.
We'll try.
but my experience is like Mike, where he's been asking for, real life examples. You learn a lot more when you're working with your own data, because you've been thinking about it, right? We're talking about constructs. Right, we talked about how we measure constructs, and you guys identified items for measuring these constructs. You've put a lot of thought into this, and so the data will make a lot more sense to you when you are analyzing your own data.
I think we do it.
So I know we don't need IRB, but how are we allowed to literally just
You just post it on your Facebook or
Okay,
whatever.
Send it to
You can send it to whoever you want.
Yep.
Yep,
Okay, because they have.
yeah,
Well, half of them be girls.
I'll talk to Jan.
Sure.
Yeah, that's true. That'd be,
I'll talk to Jan.
They're all freshmen, that's, I mean, all of it.
a lot.
That may be.
You think we can get 100?
Be interesting. You guys are, yours is gonna be the hardest.
let me ask this, maybe we should pull them up real fast.
Ours would be weakness. I can
Probably.
send it out to everybody.
If we don't get what we
But,
want,
so it would be good to.
then.
I'm just gonna look real quick.
Right?
Yeah, let's talk about what we want to.
Would
It
you
would be
do-
nice to get
Yeah.
a mix from
I think the
freshmen
dean,
to
I
seniors.
think the K-school dean will let me send it out here. That's like 85 faculty. And I think I can get the associate dean of CPMS to let me send it out.
Yeah, why not?
Maybe not to everybody, but that's a lot of faculty. And then if we get one more,
Well, I would like something to them.
Does that mean it should vary?
Yeah, that would be.
That's the largest college on campus.
I think it's.
yeah.
Okay, so you guys are doing just 2 of them or all 3?
Will you talk to
Yeah.
them?
I think we're gonna do all
We're
three.
gonna try and do all 3.
Okay. Take a look at them. If you are gonna send them to a large group of people, I think it would be interesting to make sure you have some demographic data on there. So if you're asking, have gender, have age, have, religious affiliation, other things that you think might be of interest for your research questions.
If we got 3 big colleges.
Yeah. No, we decided to because you're full.
Cause we've got level
Well, there's
one.
no references to it.
I think.
I can do a few.
I can write out,
But even other, yeah.
we do have you're in school, we have their age, but we don't have.
So I want you guys, why don't you get in your groups right now? Spend about 10 minutes. I want you to think about, take a look at your surveys. I want you to identify 2 possible statistical tests that you could use to analyze the data from your survey, right? So think about what you have questions right now. What will they look like as variables, right?
As right
And
now.
how would you analyze them?
With the test we've gone,
Yeah, with what we've covered so far.
Because it would be a female.
Yeah, it too. Would that be in the noise?
wouldn't that be tests there's only 2?
We've got some of this already here, and those questions that we asked early.
Well, actually, I have to look at
Because
the.
Anova would be if we had 3, they're only looking
Said-
at the